So we are now starting with time series analysis. After understanding the basics of multiple regression, of course, it was not only basics, but quite advanced. Now we are going to apply that into various practical applications of the financial markets, where we are going to use forecasting on a day-to-day basis. So time series, the word time series basically means over the period. So these are, the modelings or the same regression models we are going to use, but where the past or the future time will make an important, implication here. Now, of course, there are various things into the model or various things into the topic. So what I've done is that I've just summarized everything in the formula notes. You can see here trend analysis is what we are going to start with first, and then we will do auto-regressive models. This is very important, correct? Then there are few more things like random walk and unit root, seasonality, how to detect seasonality in a model, and arc and multiple time series. All of this components we will study one by one. And finally, there will be the summary of which test is applicable when. That is the final outcome. Okay. So step by step, we'll start. First, we'll start with trend analysis. Okay, so let's start time series. And the first thing we are going to understand. Now, when I say the word trend, means over the period, there is something which is going on in a form of pattern. That is what is trend, right? So let us first understand what exactly is time series. So remember some of the components that we studied, we do a time series analysis or cross-sectional analysis. Basically, time series was when I'm trying to analyze the last 5 years performance or last 10 years performance, let's say of a stock or a company. Or cross-sectional is when I'm comparing the company with others in the market, peers in the market. So here we are discussing the time series. Time series is a set of observation for variable over successive period of time. So they've given an example. For example, if you want to analyze the monthly returns of the stock of last 5 years. So basically you'll have last 5 year monthly returns, that is 60 monthly returns you'll have, right? So when we do that, what are we trying to capture? We are trying to capture a pattern or a trend. Yes, that is what our focus is, correct? This pattern or trend can be simply seen by plotting a data like a trend line, isn't it correct? On a graph. So why do we need the model? Well, we need the model so that we can utilize this in predicting the future or the forecasting. So a seasonal trend in sales is easily detected by plotting the data and noting the significant jump in sales during the same month. For example, in the December month, suddenly the sales jumps. So that can be detected by looking at the trend line, correct? Now we are going to utilize the same thing, but in terms of predicting something, in predicting the outcome of Y. Remember, our regression model is Y equals to B0 plus B1 X. Here, that X is nothing but the time. Yes, that is what we are going to study. So we are going to study two types of trend model. Number one is the linear trend model, and number two, which is very important, is the log linear trend model. Two types of trend model we will study. Individually, we'll study them and then we will compare which model is right at what time, which model is best. So here we are going to compare our linear model versus the log linear model. Okay. So those we will compare here and we will decide which model is to be used under what situation, and accordingly we will basically do the questions. Okay. So this is where we'll complete the trend mod or trend analysis, or we'll try to understand the two types of trend mod. Let us go step by step. First, we are going to understand a linear trend. Linear trend means the trend is going in a direction. It might be going downwards or upwards. So linear trend time series is a pattern that can be graphed using a straight line. Downward sloping or negative trend, and upward sloping means a positive trend. Now, this trend depends on the slope. Okay, so I will show you how. So for example, this is a regression model, but what you will notice unique, what is a normal regression model was Y equals to B0 plus B1 X, right? Here, instead of X, you will notice you have the time. That is what the unique thing in the trend analysis or trend model is. So let me show you directly here. This time can be 1, 2, 3 or any time. So this is how we are going to predict the model. So very easy, nothing complicated out here. How do I use this into the prediction? The time can be anything, 1, 2 or 3. For example, if they give me the time is 2, I will replace that x with 2 or 3. Okay, if they give me 2, I'll replace with 2. If they give me 3, I'll replace with 3. This way you can find the value at any time. For example, suppose they've given me a trend model here with B0 and B1. So what will my model translate into? The predicted value of Y will be 1.70 plus predicted value of B into the time. Yes, this will be my regression model. Okay. Now this time they will provide me T1 and T2. So if it is T1, I'll replace the T with 1. So when time equals to 1, what will be the prediction of Y? Y, I will get 4.7. When time equals to 2, I'll get 7.7. You will notice the difference between both is equal to the slope. The difference between each period is due to the slope. Right, right, right. So the difference is nothing, but it is 3, which is the value of the coefficient, that is slope here. Am I correct? Right? Right, right. Now this, since the slope is positive, the trend will be upside or upwards trend, right? So for each time period, the value will keep going up, up, up. But let us take a more practical approach where we will take a more complex model. So here they are trying to analyze the time series for manufacturing capacity utilization. So we are going to forecast the capacity utilization. Now they have given us the manufacturing capacity utilization in percentage. But guys, this is not a forecast. This is the actual outcome. Got it? So this is the actual outcome from Q1 all the way till Q14, right? Time till 14. And they've given us the outcome here as well as here. This is nothing but these are my actual outcomes, correct? Now, applying the methodology to fit the linear trend model to data procedure, results are shown. So we have the regression model B0 plus B1T, and there they've given us the component R square, adjusted R square and all. Observations are 14. My coefficients are this: intercept and slope. You will see negative. Guys, negative means will it be upward or downward trend? Everyone in the class? I'll write down the equation by that time. It will be 82.137 minus 0.223 times the T. Will it be upward or downward trend, everyone? Everyone, can you confirm? Since the slope is negative, the trend will be downward. The predicted value will keep going down, down, right, right, right. So see, based on this information, predict the projected capacity utilization. So we are going to predict the projected capacity utilization. We have the actual. And you know the difference between actual and projected is what we call as error, right? So see, this is our equation. We will keep the T for one period. We'll get the value. This way we can find the value for each. Now for the first period, where T equals to 1, we will simply use this model and replace T. We get the projected value as 81.914. This is my projected value, correct? But they've also provided me with the actual value, isn't it? Now, what is the actual value? See, actual value was 82.4. Am I correct? Here it was 82.4 for first period. This way we will find the difference between projected and actual value for each. So what is the difference between the outcome that you received and what was projected? That is what we call as the error. Error for first was 0.486, right? This is how we get the error. Error is the difference, correct? Now, if I put the projected trend line, right? Of course, you know, the actual and the projected won't be the same, correct? So since the actual measured value is greater than the predicted value, the error term is positive. I got the error term here as positive, everyone in the class. Why? Because the actual value was more. Of course, it can be negative also. So it's not that always it will be positive. It can be negative also, right? This way, they've done the comparison for all the quarters. Okay. You can also find the same thing between the predicted and the actual. Okay, mostly you will see the trend can be anything, but here the projected value will be downside only because, and it will be in a trend line because the slope is negative. So when I look at the graph, okay, you will notice the graph. What is this? The black one, is it projected or actual? The black one that you see here, guys, the black one is the projected one, and you will notice it is moving downwards. Why? Because the slope was negative. The actual, however, is not going in a trend line. And the difference between both, which is the highest here, the highest difference that they've also highlighted, this difference between the both, for example, this difference, this gap between the projected and the actual is what we call as residual or error, isn't it? So this is nothing but my error, or so-called as residual. Correct? The difference between, which is the difference between the actual minus projected. Understood? So we utilize the linear regression model. The predicted values by definition fall on the straight line, predicted values, but the raw data does not display a linear relationship. So the actual data is not as per the trend line. There's a big difference between the projected and the actual. So our model is not that fit. It's not doing the job that I wanted to, right? Because the model is just showing me a linear trend, but the outcome is not linear, isn't it? Correct? So the model will probably not do a good job of predicting the future value. I cannot rely on the model. Isn't it clear? Now we will see what is the alternate. The alternate is log linear model. We will see that in a moment. But what I wanted to say that if there's a linear model, all you do is that replace the independent values by the time. That will give you the projected outcome. Everyone aware with the linear model? Easy? Understandable? Any doubt with the linear model? Correct? No doubt, right? Right, right. So what we are going to do is that we are going to understand how does a linear model look like. So first thing, we are understanding the linear model. Easy. So I will write here the linear model, lin model, and then we will understand the log lin model. Okay. Something of this sort was there in level 1 regression at the end. So linear model where we are trying to predict y based on b0 plus b1. Instead of x, I'll put the value t plus error. Okay. I'm not putting here the value of error because when we actually apply, the error is missing. However, when they ask us error, error is nothing but the difference between the actual and the predicted. Correct? This is my lin model or linear trend model. This is under the trend models. Okay. There are two types of trend models, linear and log linear. And now we will understand when am I supposed to use the log linear model. Sometimes the linear model will not do a correct job in predicting the outcome as what we just saw in the manufacturing example, where the trend line is going it's going in one direction, but the actual capacity utilization is way different. So the model is not useful for predicting the future. It's not going to give me an accurate outcome. Now we will use the alternate option here, which is called the log-lin model. Log-lin model. When do I use this log-lin model? Again, it's a time series model, but very unique thing is that it displays exponential growth. See, many students get worried. What is log and what is exponential? Let me tell you, exponential, whenever you do exponential of something, it's a continuous compounding. And log is the opposite of it. Log of x is the opposite of it. So if you do something continuously compounding, you get so for example, if I do x, continuous compounding x will give me the value, which is e to the power x, exponential. But when I do the log natural of e to the x, I will get the value of x. This is the mathematics property. So guys, when you do continuous compounding of x, you get the exponential value. But from exponential, you want to bring it back to the normal, you do the log natural of it. Okay. So time series, particularly financial times, now even if you don't know this, it's okay. So it displays exponential growth with continuous compounding. Positive exponential growth means the value will keep on increasing at a constant growth rate. So every period, the value will keep on increasing. This positive growth, exponential growth means if we plot, it will look like a convex curve. Remember, positive exponential growth has convex, but negative exponential growth means it will look like a concave. Okay, so whenever the growth is positive, the graph is convex. Just remember this for your important, theoretical question. Whenever the growth is negative, the graph will be concave. Okay, no one's going to ask you the graph, but just in case if they ask these points, right? Now, if you see in the log linear model, what is a normal model? Y equals to b0 plus b1x, right? So here you will see a unique thing. My log linear model looks like this. Y equals to exponential of b0 plus b1x. Now, instead of x, I will put t. So what is my log linear model? Here we are going to predict the y. Okay. So the y for, let's say, period t is b0 plus b1 times t, but it is the exponential of it. Understood? Now, since this value of y will be in terms of exponential, we need to convert it into the normal method. And how do I do that? So see, I've already told you here, log of any exponential will give me the normal value. So when I do the log natural of exponential, I'll get the value of x. So when you do the exponential, when you do the log of the exponential, it will give you the value. So x here, remember that x is nothing, but in this case, the x in my model, the x is b0 plus b1 times t. If I do the log of this exponential, I'll get the value of x. So what will get translated? Suppose now if I'll do log on both sides, so here I will do log of yt equals to log natural of e to the power x. Here I say x is b0 plus b1 times t. Time, it's a time series model. So when I do log on both sides, the model translates as log natural y of t is equals to log of exponential of x will result into x. So this will get translated into b0 plus b1 t. Now the model becomes perfect. So now, if you see the conclusion, the linear model is this, and the log linear model is simply where the y has become the log natural. Understood? This is the final outcome. Clear? So now if you will see here, they have given me the original model where we take the exponential value. But when I translate by putting log on both sides, this is what eventually I will get. I'll get log of y is equal to b0 plus b1t. Understood this part, everyone? Correct? Right? So what have I done here? I have actually transformed. Yes, when I say I have transformed the model, which means basically we have transformed the data which produces a linear trend line with a better fit for the data. Yes, by converting the values into the log natural of y, we have transformed the equation. So the model defines now y, the dependent variable, as the exponential function of the time. Exponential function of time, correct? So the model defines, I'll repeat, y, the dependent variable, as an exponential function of time, the independent variable. Rather than try to fit the non-linear data with a linear regression, we take the natural log of both sides, which we just showed, and now the equation has been transformed from an exponential to a linear function. So by doing log on both sides, we have transformed the equation from exponential to linear, exponential to linear. Remember the equation originally, this was in exponential form, right? We converted or transformed that into the linear form. Now, how do I apply this? We will see a very nice example, right? So here, an analyst estimates a log-lin model using quarterly revenue data from first quarter to the fourth quarter. Okay, so this is the model log of the dependent. If you will see log of the revenue, okay, equals to b0 plus b1 t. The last t here was 48. Okay, that is the these are what my quarterly revenue, correct? Correct. Okay, the results are shown as follows. They've given us the intercept and the trend. Now, if I use this intercept and trend, what will my model look like? My model will be log of revenue equals to 4 plus the slope, that is 0.09 into T. Now, they wanted me to predict the revenue in the first quarter of 2024. First quarter of 2024 means T is equal to 49 because previously we were given 48 observations. So our year, we were already having the data for 48 observation in the original model. Now we want the next quarter. So my T will be now 49. So if I want, the original model is B0 plus B1, that is 4 plus 0.09 T. Now we are looking for the 49th quarter. So then my answer will be log natural of revenue is 8.41. But guys, what does this 8.41 mean? So if you do 8.41 and then if you convert this into an outcome, now how do I convert log into a normal thing? Guys, in your calculator, you will do 8.41 and then press second ln. Yes, press second ln, everyone. So what we will do, we've got the value of log natural of revenue equals to 8.41. Now, if you want to convert this into revenue, you need to do the exponential on both sides. So exponential of this will give me revenue. So I will have to do exponential of 8.41. So when I do that, I'll get 4491.2 million or 4492 million, right? You'll get the value 4491.76, or you can say 4492 million. This is how you will have to do one step extra by converting the final outcome, which is in log natural, to a normal number. Okay, so you do exponential on both the sides. Clear, everyone? This is how we use the log lin model. So two types of model: linear model, where just time is the factor of independent. In the log natural model or log lin model, we will use the independent as the log. So we'll get the value of independent as log. Then we will convert that into a normal by taking the exponential of it, right? Now the question is when to use which. Okay, that is an important question. That is what we are going to address, and we'll see questions related to it. So to determine if a linear or log linear trend model should be used, the analyst should plot the data. Remember, we discussed that if there is a trend, if there's a trend line, okay, then log linear will not be, then the linear model will not be correct to predict or forecast. So when should I use linear and when should I use log linear model? Okay, let's see that. A linear trend model may be appropriate if the data points appear to be equally distributed above and below the regression line. Means they are not following a trend. For example, they've given the example of inflation rate. Inflation rate can increase or decrease, right? Correct? So that I can use with a linear trend model. But when the data plots with a non-linear shape, if the data plots with a non-linear shape, then the residuals from the linear trend model will be persistently positive or negative. So we saw in the example that here when a slope was positive or negative, in that case, what happened? In that case, the data showed us a trend line, either upside or downside. We did the example where we saw the downside trend here, correct? Now, in such a case, we cannot use the linear model. We already discussed that. So in this case, the log linear model may be more suitable. Why? In other words, when the residuals form a linear trend model are serially correlated. Remember serial correlation or autocorrelation. That is a violation of the assumption, isn't it? Correct? So a log linear trend model may be more appropriate in such a case. Otherwise, you will have autocorrelation or serial correlation, right? So in other words, when they have mentioned by taking the log of the variable, a regression line can better fit the data. Most of the times, financial information or financial data like the stock prices or stock indexes and company sales are often best modeled with a log linear. For example, which we saw revenue, forecasting revenue or EPS or any other financial number or even the asset prices. In such a case, a log linear model is more suitable, right? So you have both the models, linear trend model, for example, for inflation, which can increase or decrease. Log linear model is generally used for mostly for asset prices, right? Linear trend model also, can I use it for exponential growth, or can I use it for log normal? What exactly and when will I use? So they have mentioned here, the left panel is a plot of the data that exhibits exponential growth along the linear trend line. So if I have exponential growth with linear trend line, okay, then what will happen? It's better I use the log linear model. So the panel on the right of the plot of the natural logs of the original data and a representative of log linear trend line. So this part is a log linear trend line and this is the same linear trend line, correct? Which is a better model? Okay, if there is an exponential growth trend line, then which one is a more fit and accurate? In such a case, the log linear model is more fit and accurate. The log linear model fits the transform data better than the linear trend model, therefore yields more accurate forecast. Remember, whenever there is a exponential growth, the log linear model will show a much better outcome. Okay, this is our linear model. This is a log linear model. That's more fit and accurate. So what is the conclusion? When should I use which? Just I will put the conclusion out here. Whenever there is an amount or whenever there is a growth rate. Okay, see this. When should I use which model? So the bottom line is that when a variable grows at a constant rate, a log linear model is more appropriate. So when it is growing at a constant rate, when the growth is constant, we use a log lin model. Okay. And when the variable increases over time by a constant amount, so whenever the increase it's in terms of constant amount, whenever the growth is in constant amount, in this case, we use a lin model or linear model. Just write down this for your reference. Very important from your exam point of view. Correct? Which model is useful and when? Whenever the growth is in constant amount, okay, then so whenever there is an increase of constant amount, we use a linear model. But whenever there is an increase in a constant growth, we use a log lin model. Okay. Now also remember, we discussed that the log lin model takes care of the autocorrelation. But what is autocorrelation or serial correlation? The problem of serial correlation, that is one of the limitations of the trend models. Okay. The assumption underlying the linear regression is that the residuals are uncorrelated. But here you will say that, sir, the residuals are correlated, isn't it? Because last year's outcome will be used to predict the next year's outcome, isn't it? So the violation of assumption is referred to as autocorrelation, right? For this, we are going to use a separate model if there is an issue of autocorrelation. In this case, we will use a model called AR models, which we will just see in a moment. Whenever there is the issue of autocorrelation, we will use AR models. What is AR model? We will just see it in a moment. Okay. The presence of serial correlation in residual indicates that the model is misspecified. Yes, whenever there is autocorrelation or serial correlation, we have misspecified the model. Okay. This is a significant limitation as it means that the model is not appropriate for time series and we should not use it to predict the future values. So there's a high chance that the trend analysis model that we use has the problem of serial correlation or autocorrelation. Still, we use the model, and which model is fitter amongst the two? We use the log linear trend model. It is still better than the linear trend model whenever there is a constant growth rate. This is the bottom line. Please highlight this. Most important thing. Even though the trend models has the problem of autocorrelation, we still use the log linear model. Whenever we have an exponential growth, we use the log linear model, right? It may be the case that even the log linear model is not appropriate in the presence of serial correlation. In this case, we will want to use autoregressive model. So remember, in the index here, I have told you we are right now using trend model. But whenever there is a problem of autocorrelation, we will use the autoregressive model. Now, if you remember carefully, whenever we had this problem of serial correlation as a violation of the assumption, we use a Durbin-Watson test, okay, DW test, correct? So DW test was used to detect the violation of autocorrelation. In fact, we use the four different types of tests. We use the Brosh-Pagan test, Brosh-Godfrey test, right? And amongst that, we use the DW test to detect autocorrelation. Okay. This DW test will tell us whether there is an autocorrelation or not. Durbin-Watson test. Now, what is the conclusion? The conclusion is that there is a number if the DW is equal to 2 or not equal to 2. That is the hypothesis. If it is not equal to 2, then there is autocorrelation. Let me put up that here. Recall from the previous topic that the Durbin-Watson test is used to detect autocorrelation. So from a time series model without serial correlation, DW should be approximately equal to 2. So if it is 2, there is no autocorrelation. I'll write, if it is 2, no autocorrelation. But if it is not equal to 2, there is autocorrelation. So if the DW is significantly different from 2, greater than or less than, then there is autocorrelation. Then the model is not fit. I cannot use that model. Understood, everyone? Clear? 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 In fact, you will see that we use various other tests. Amongst that, I'll just show you that for serial correlation, we use DB test for a single lag. Here is a single lag, right? We are just going one step back. For multiple leg, we use Brosh-Godfrey test, but here they are not going to discuss about the Brosh-Godfrey test. They have just used the Durbin-Watson test, which is for a single lag. So here also, if you will notice in our model, we have a single lag. We are just going one step back. Okay, so just remember to test the fitness of the model. Okay, so here in the formula, we will write that for the log-lin model, we will write A. This is my linear trend models, A and B. And now we will write to test the fitness of the model or to detect autocorrelation. So to detect autocorrelation, which test do we use, guys? We use which test? We use a test called Durbin-Watson test, DW test. Okay. And in the DW test, we do not have to do the test. We just have to see the outcome, whether the DW is equal to 2 or not equal to 2. If it is equal to 2, then there is no autocorrelation. No autocorrelation. That means our model is fit to use. But if it is not equal to 2, greater than or less than, then there is autocorrelation. So the model is not fit. We cannot use the model. In this case, we will say the model is not fit to be used. Okay. Then what is the solution? The solution, we will see that we will go for another type of model, which we will see in a moment. It's called the AR model, autoregressive model. We will see that in a moment. But let's first do the questions related to the trend model, because everything about the trend analysis we've done. Linear, log linear, we compared and understood the limitation of autoregression and detected the autocorrelation uh, using the DW test, right? So let us see example related to it and let's see if we are able to solve it. Okay. So here is the example and we have 1, 2, 3, 4, 5 questions related to it. Okay. So let's start with the first information. Consider the results of the regression of the monthly real estate loans. This is going to be in dollars, right? So this is my Y. Okay. In dollars, this is going to be my Y. By commercial banks over the period for January 2020 through all the way till September 2023. So 12, 24, 36, and plus 9. So 45 is my time, last time. Okay. This is my model. Okay. R square and all observations are 45. Durbin-Watson test is not equal to 2. Okay, so there is a problem of autocorrelation. Coefficients and the intercepts are given to me. Guys, if I were to replace that into the model, how will my model look like? My y0 here equals to b0 plus b1 into time, correct? So I will write my y is equal to b0. My b0 here is, I'll just replace the values. 1195.6241 plus b1, that is 12.230448 into the time, whichever time they tell me, right? I'll multiply that with the time so that I will get my loan, the monthly real estate loan value in billions of dollars. Okay. Now, let me show you exactly where it is. See here, fourth question. The forecasted value of real estate for October 2023. So till September, there were 45 months, correct? Till September, there were 45 months. So when I'm going for October, I will multiply with 46. So my T will become 46. That's the only thing. So in the model here, you will multiply with 46. So if you do this, 12.230448 into 46, store 1, right? Plus 1195.6241. That will give you an answer. Are you getting an answer? 1758.22? 1758.22. Everyone, these many billions of real estate loans will be there. Everyone, correct? Got it? Everyone got the fourth answer? Easy, right? Okay. Now, let us see the regression of the real estate loan against time is a trend model, AR model, or ARC model. Now, of course, you will say trend model because you have no idea what is an AR model and ARC model, but later on we'll study both of them. So this model, which is based on time series, that's a trend model. Okay, very easy. The rest of the two models you might not be aware. We'll discuss that later. Now they are asking the result of the estimation indicate upward trend or a downward trend. Of course, the only choice is upward here. The rest two are related to the other model. But why do I say upward trend? Guys, can someone tell me why is that we say upward trend? Because if you look at the slope is positive. So for every month, the value will keep going high. Got it? So the trend will be upward. The more the time, the higher will be the value. Everyone understood this? Right? Okay. Now, very interesting. Are the intercept and the slope coefficients significantly different from 0 at 5% level of significance? So for this, we have to test the significance, okay, for slope and coefficient individually. Now, for slope and coefficient, how do I test the significance? We have been given the standard error. Now, actually, we can use the Durbin-Watson test, but the Durbin-Watson test is for the overall fitness and to test whether the model is having autocorrelation or not. For a normal testing of the slopes and coefficient, since they haven't mentioned anything, we will use a t-test. T-test. Yes, which test we will use? T-test. Okay. And what was the test statistic for t-test? Just let me remind you the test statistic for t-test. For testing the coefficient, I will write. This is for overall model fitness. Okay. I will also write for testing to detect the autocorrelation. This is fine. We will use this. But they haven't mentioned all this, unfortunately, in the notes. We will just write it here. For testing the coefficients, for testing coefficients, we will use a normal t-test. A t-test can also be used if nothing is mentioned. T-test, what is the test statistic here? We look at the value, the target value, okay, and the mean or the coefficients divided by the standard errors. So we look at the coefficient value and we are testing the significance. So the target is always 0 divided by the standard error. So eventually it is the coefficient divided by the standard error. When we do this, we get the t-test test statistic. Okay, we get the test statistic. We will compare and we will test whether the coefficients are significantly different from 0 or not. So if this t statistic is greater than the critical value or less than the lower critical value, greater than the higher critical value and lower than the less critical value, okay, lower than the negative critical value, then in that case, we will reject the null. We reject the null. And whenever I say we reject the null, what is the null here? The null here is that the coefficient is 0 and the alternate is not equal to 0. Correct? So this is what the outcome will be. So greater than the, I'll write down the higher critical value and lower than the lower critical value. Okay. So then if it is greater, then we will reject the null. Now, unfortunately, they expect all the students to know from level 1. That's not fair, but still. Okay. So here, how do I find the test statistic for both? You will simply take the coefficients divided by the standard error. That is how you'll get the test statistic. So 1195.6241 divide by 8.9704362. You can just round it off. It is going to give you 133. Am I correct? Rounding off. Same way, you will do 12.230448 divided by 0.3396. You'll get around 36 approximately, correct? Now, they have not given us the value. Mostly you will get these value from the distribution table that they will provide you. But just for your reference, here, my degree of freedom for a t-test, my degree of freedom here is going to be n minus 2. Remember here your n is 45. So my degree of freedom will be 45 minus 2. That is 43. Yes, I will write down here. My degree of freedom is n minus 2. Whenever this is similar to correlation test. Whenever we were testing any coefficient like correlation, it was n minus 2. So here also we will take n minus 2 and the significance at 5%. You will get those values from the distribution table. Actually, the coefficient value is 2.02 or 2.09 to be precise. But do not worry about it. You know the z value for 5% is 1.96. That's approximately 2. And these test statistic values are way higher than 2. Okay. So definitely we reject the null. Null was that they are not significant, means the value is 0. So we reject the null and we can conclude that yes, not one, but both of them are statistically significant. Am I correct? Both are statistically significant. So in both of this case, we will conclude that we reject the null. Reject the null. Okay. I'll repeat. Unfortunately, this is not mentioned in the notes, but they expect students to know this from level 1 regression model. Okay. Next, the analyst has determined that the monthly sports utility sales in US have been increasing over the last 10 years. So it's a trend model, but the growth rate has been relatively constant. Okay. So constant growth rate goes for which model, guys? Can you tell me? If it is about a constant growth rate, should I go for linear model or log linear model? Everyone in the class, I should go for log linear model, correct? So I will look out for log linear model, which is the appropriate. First one is a linear model. Second one is a log linear model, correct? This looks like, but let me look at the third one. Third one is also log linear model. What's the problem? In third one it is based on previous year. Now this is not an incorrect model, but these type of models are called auto-regressive AR model, which we will just start studying now. But this is an AR when you're using the past, or when you're using one period before to predict the later period. Okay, that's an AR model. So C is a different type of a model. A was a linear model. B is a log linear model. And why do I use the log linear model? Because they said constant growth. That gave me the key that I will use a log linear model. Understood? Correct. This is how a case study for the linear models will look like. Clear? Till this part, everyone? Okay. Yes. Yes, under the auto-regressive model. Now remember, when we use the trend analysis model, the independent factor was time. Now, what if I'm using the previous year to predict the values of the current year, or I'm using the current year to predict the value of the next year, or I'm using the next year value to predict the value of the further years? So this is where the dependent variable is regressed against the lagged value. Lagged value means the previous year values. So when the dependent variable is regressed against one or more lagged values of itself. So let's say the value of the index today is based on the value of the index last year. When that is the case, it's called AR model or auto-regressive model. For example, the sales of firm could be regressed against the sales of the firm in the previous month. So here, guys, my xt is b0 plus b1 x t minus 1, t minus 1, past year. And same way, if I want to predict x t plus 1, the futuristic, it will be based on current. But what if I want to predict the past, t minus 1, then it will be b0 plus b1 x t minus 2. This is the way I predict, it will be based on the past. But if I want to base on the future, we will use x of predicted value of x in t plus 1 next year. So in this case, it will be b0 plus b1 xt, current year information to predict the value of the next year. Okay. This is going to be my auto-regressive model where you will see current year value based on the lag, one lag variable. You can have multiple lags also. In the syllabus, as of now, we have only one lag. Okay. In an auto-regressive time series, past values of the variable are used to predict the current value. Okay. But can we use this? Immediately the next question is, won't we have autocorrelation or won't we have a serial correlation? Yes, there is a high possibility of it. So under what condition can we use this model? We can use this model only if the model is covariance stationary. Now remember this word, what is covariance stationary? Covariance stationary means it has to meet the three conditions. What are the three conditions of covariance stationary? First, what are the three parameters? You all know the mean, the variance, and the covariance or correlation, right? Now, these three parameters, they should be constant and finite. Constant and finite. Okay, see this. So what does it say? The expected value, that is a mean, is constant over time, or the volatility around it mean does not change when it's constant, and the covariance between the values at any given lag is also constant. Now you might be wondering what exactly it is. Just remember, covariance stationary is a property of the parameters. If you meet this property, then the model is reliable. You are good to go with the model. You can use the model. Otherwise, the model is invalid. So the model should meet all these three properties. It is somewhere related to your level one, concept of uh, where we discussed what concept basically, in level when we did a concept of where we were discussing about the confidential intervals, right? So central limit theorem, yes, central limit theorem is the property where we will use the model if it meets the parameters. So here also same way, covariance stationary is the quality. If you meet these three conditions, then you can use the model. Okay. So, of course, there will be issues with the model, especially serial correlation. So, what should we do? We did a DW test for trend analysis. Here also, we will detect the issues and we'll discuss. But before that, let us use the model. So, here you will see that now you will see regress not with one lag, but two lags. So, B1 xt minus 1 and xt minus 2. This is more than one lag. So, if you use one lag, it's called AR1. If you use two lag, it is called AR2 model. Here you will see 1, 2, and so on. Number of lags. So then I will say ARP. P here because they've used P, so I will use P. Depending on how many back years you want to go, those many lags are there. Okay. Mostly you will get AR1 model, but AR2 is going 2 years back. AR3 is going 3 years back. Okay, so here the P indicates the number of lag values in the model. Got it? Everyone? We will now use the model and see how it works. So autoregressive model are used for forecasting. Let us see the model. Here, this is both of these are AR1 models, right? You see this? This is where we are going one period back. Understood? One period back. Correct? A one period ahead forecast for AR1 model is determined using the following. So I'm predicting one period ahead. But using that one period, I'm predicting the second period ahead. So how do I predict the second year? I will take the current value to predict the next year value to predict the further next year. This way we use it in a chain. This is why it is called chain rule of forecasting, because you will have to go to the second year, not directly. First, you'll have to go from current year to the next year to then the further years. This is how we will use the AR model into forecasting step by step. That's why it's called chain rule of forecasting. Okay. So let me show you that how it works here. Suppose that the AR1 model has estimated and produced the following prediction. Okay. This is current year based on the past. Calculate a two-step ahead forecast. So I want to test T plus 2. So if I want to predict X, this is what they want me to predict, X T plus 2. Okay. So that is based on T plus 1, isn't it? So it will be B0 plus B1. B1, I will say B1 X T plus 1. But before that, I first need T plus 1, right? So first I will predict X T plus 1, which will be B0 plus B1. And that will be based on X T, current year T. And before this, I'll have to predict X T. So first I'll have to do this, and then this. Understood, everyone? Right? They've given us the value of X is 5. So I'll place 5. Okay, current value of X is 5. So I have got XT as 5. Current value of X. So this is my XT equals to 5. So I don't need the previous one. I can directly find. So I don't need this. They've provided me this. So I will first find the next year value, then the further year value. So I will place that in the equation here. I have the B0 and the slope into 5. That will give me XT plus 1. Using this XT plus 1 in the model instead of X, I will use that and I will get the value again. You will see the value because the slope is less than 1. You'll see the value is less here. Got it, everyone? How you will find out in sequence. This is how we use the AR model. Everyone understood? Correct? Right? Right. So AR models, what are we discussing about the AR model? We discuss what is the basics. We discuss the three conditions of covariance, stationary, and the structure of AR model and how to use that into forecasting. So basically, I will use here the auto-regressive model or AR model. So what is an auto-regressive model or so-called as the AR model? Okay. It is based on the lagged values. So here the value of xt is based on b0 plus b1 xt minus 1. Okay, this is my AR1. Okay, where I've used one lag. So I will write this is AR1. If I want to use AR2, then I will find the value as B0 plus B1 X plus, then for 2 lag, I will go one period back, correct? So not only one period, I will go 2 years back. So that is what we call as AR2. So I will have B1 and B2X. This will be T minus 1. This will be T minus 2 and so on. This way you can keep going on and on, right? Correct? So we use this to forecast. This is called chain sequencing, or this is called chain rule of forecasting, right? Now, this is just how we use the model, but the model needs to fulfill the three covariance stationary criteria. Okay. This is called chain rule of forecasting. If not, then we cannot use the model. Okay. Of course, we are going to test the model also in a moment. So, how to test whether the model is fit or not? Because see, remember, any trend analysis model or any model which is based on the past of the same, there is a high chance of the violation of the assumption, which is the serial correlation or autocorrelation. In such a case, what should I do? We already discussed that for the previous case, we did a test. We did a DW test, right? Here, are we going to use a DW test? Well, you can use a DW test, but they have a different test here, which is like a T test. First of all, when the AR model is correctly specified means it meets all the covariance stationary property, right? Then it will not exhibit serial correlation. See, what is serial correlation means the error terms are positively or negatively correlated between the periods. When the error terms are correlated, definitely the model is unreliable and the t-test of individual coefficients incorrectly show statistical significance means this will result in which error? If you recollect, guys, it will result in type 1 error. Means by mistake it will tell me that the coefficients are significant. Type 1 error is rejecting a true null. So if the residuals have significant autocorrelation, the AR model is not reliable. We already know that. So how to test whether the AR time series model is correctly specified? There are three steps for that. So we are testing whether whether the AR model is correctly specified or not. So to do this, it's a three-step process. So testing this, we are going to use a three-step process. It's a very different test. We are not going to use a DW test here. Okay. The step number 1, 2, and 3. Out of this, honestly, it's the third step, which is the crucial. First step, they are saying us that estimate the AR model that you want to evaluate. So first, here we will estimate the model. We will estimate the AR model. Okay, which can be AR 1, 2, 3, any model. And then we will calculate the autocorrelation. Now, this autocorrelation calculation is nothing but calculating the error. Remember, error is generally the difference between the actual value and the predicted value, right? So here we have used the AR1 model, okay? And then they said calculate the autocorrelation means the model's residual. Here, the residual means we are testing the level of correlation between one period to the next period. Do I have to do that for my exam? No, you do not have to calculate the autocorrelation. They will provide you. Okay. Third step is what I have to do is that test whether the autocorrelations are significantly different from zero. So when I'm going to test the autocorrelation, I will write autocorrelation. I'm just writing autocorrelation as AR, not autoregressive. So I'm just writing autocorrelation short form here. So when I'm going to test the autocorrelation, I have to test the hypothesis whether this autocorrelation is significantly different from zero or not. So whether it is zero or not zero, this is what is going to be my major test. Well, what is the outcome here and which test am I going to use? We are going to use a t-test. So if the model is correctly specified, none of the autocorrelation will be statistically significant. Statistically significant means they are not equal to zero. So guys, if they are not equal to zero, is my model correct or incorrect? So yes, what is the outcome here? If the AR, when do I say the model is correctly specified? The model is correctly specified when none of the autocorrelations are statistically significant. Means if I fail to reject the null, then I say the model is correctly specified. Then I say the model is correctly specified. Okay. Remember here, you do not want to reject the null. If you reject the null, that means there is autocorrelation. So if you reject the null, I'll repeat, when you reject the null, the alternate is accepted. That means autocorrelation not equal to 0 means there is autocorrelation. Understood? So what do I want? I want the model, for the model to be correctly specified, I want it to fail to reject the null. This is what I want. Everyone understood this or not? This is very unique compared to other models. So if I reject the null, if the null is rejected, that means autocorrelation is detected. That means the model has autocorrelation. Autocorrelation means I cannot use the model. Understood, everyone in the class? Correct? Now, for this, I will require a test, and we are going to use a test, which is a t-test. So instead of Durbin-Watson test, we are here going to use a t-test. T-test. Now, this t-test is unique because you will have the test statistic, which is the estimated autocorrelation divided by the standard error. They will have given you what is the standard error and what is the degree of freedom. I will write down all here. So the test that we are going to do is called the t-test. Okay. Now in the t-test, two things they have given us is the test statistic. I will write down here. For the t-test, I will be provided with the test statistic. So the test statistic and the degree of freedom. Okay. Degree of freedom, I'll write degree of freedom. They have provided me degree of freedom as t minus 2. Remember here, it's not n, it's a time. So it is t minus 2. And the test statistic is autocorrelation divided by standard error. And standard error is inverse of the root of t. Check here the formula. Test statistic is autocorrelation divided by standard error. And what is standard error? Inverse of square root of t. Okay. Degree of freedom is t minus 2. T minus 2. See, they have mentioned why not Durbin-Watson test? Well, you can use it, but they are saying it is not appropriate for testing serial correlation under autoregressive model. Therefore, we use t-test, not the DW test. Now, although we've written everything out here, let me show you here exactly how it works. So then we will be able to analyze whether the model is fit or not. Okay, let's see this. The correlation of the error term from the estimation of AR1 model with a sample of 102 observations. So 102 observations. This is going to be my T. This is going to be my T. So guys, what will be my standard error? My standard error is 1 over inverse of T square root. So 102 square root and inverse, you will get the value as 0.099. Store it simply somewhere. Easy. Then they have given me the model. Okay, this is AR1 model, autocorrelation, and I have the standard error. Test statistic is provided to me. Okay. For all the lags, they have provided me this. Again, autocorrelation and the T statistic is provided to me, right? Now, just to confirm, if you use the first one, 0.06161114 divided by this, you will get 0.6225. So this test statistic is already provided to you. It is autocorrelation divided by the standard error, which we've already calculated. So they've already provided you the t-stat. You do not have to do that. There's a high chance in exam they will provide you that. Okay. Now, all we need to do, so this way they have done it for all the lags, all the lags, all the lags. The standard error is provided. For lag 2, we will get it in the same manner. We will take the autocorrelation divided by the value and we'll get the same answer. So all the AR divided by recall 1, you will get these values, right? Now, we need to find whether they are significant or not. Remember the null, I'll write down the null hypothesis and the alternate. Okay. The null is that the autocorrelation is equal to 0, which is what I want. and the alternate is not equal to 0. Now, for there to be no autocorrelation, my test statistic should not be rejected. So it should be within the range. It should be within the critical value range, isn't it? It should be within the critical value range. Only then I will fail to reject. Okay, so I'll have to check whether that is not too high or too low. So they've told me the critical value, two-tail T value, 5% significance and 100 degree of freedom. Why 100? Because my degree of freedom is T minus 2, that is 100, and 2 minus 2, that is 100. This value they will provide in exam, it is 1.98. I'll have to check whether the value is within that 1.98 range or not. So if you see all of these values are within 1.98 plus minus, if yes, then you are comfortable to go, then you will fail to reject the null. Okay. So the test statistic indicate that none of the autocorrelation in the previous figure is statistically different from 0. So because their values are within 1.98, there is sufficient reason to believe that the error are not serially correlated. That means my model is fit. Understood, everyone? Clear, right? If it is within the range. So if it is within the range, there is no autocorrelation, correct? The t-test indicate that any of the autocorrelation are statistically significant only if the value is above plus 1.98 or below 1.98, right? So if that happens, then I will conclude that the AR model is not specified correctly and I cannot use the lag values. So then the model is not reliable. So then the additional lags are included in the model and the correlation of the residuals are checked again. This procedure will be followed for each of the lag. Understood, everyone? Clear? So basically in this case, I won't fail to reject the null. Correct? Only then I can testify whether the AR model is correctly specified or not. Everyone understood this point, right? We will do some questions related to it, but we will do the questions along with this, with the few more things that we are going to understand. However, let me see if we can do some of the questions based on the backside that they've provided. Okay. Now see the first and the second question. I'll first go with the second question. Given the prediction xt 1 lakh, what is the forecast value of x2 if xt1 is already provided to me? So with xt1, I will get the first I'll get first the value of xt. Am I correct? Using that xt, I will get xt1, xt plus 1, right? And then using that, I will get xt plus 2. So then to find xt plus 2, I will then use this 5 plus 1.75 into something. So first I will do 5 plus 1.75 into, first one is 1.65. Then I'll get a value. Then I'll do 5 plus 1.75 into that value. So let us see that. What is that value? 1.65 into 1.75 plus 5. You will get a first value of, everyone, 16.5. My mistake. Sorry, it's 16.5. Yes, 16.5. Sorry, 16.5. So you will do 16.5 into 1.75 plus 5. You will get a value of 33.875. 33.875. You will use that value here. So you'll use 33.875, correct? Times 1.75 plus 5. You'll get 64.28. Are you getting that value? 64.2813. 64.2813. So multiply that with 1.75 plus 5. You will get 117.49. That is change sequencing. This is how you reach here. Got it, everyone? Clear? Easy? Now remember the three properties of covariance stationarity, that the mean should be constant, the variance should be constant, and the covariance should be constant, right? Now, is the time series likely to be covariance stationary? Here you will see the annual data and the year. So along with the year, the values are increasing. Am I correct? So the annual data. So is it covariance stationary? No, it is not covariance stationary. Due to homoskedasticity? No, covariance stationary is due to mean, variance, and covariance. So first of all, it is not covariance stationary, and the answer is due to non-consistent mean. The mean is increasing. Understood, everyone? Clear? Right? How to use the AR model? Everyone till this point? Easy? Okay. Yes. Right? Okay. Everyone till this point? Perfect. Now we are going to discuss few more things related to AR model. Okay. Basically, what if the model has the value similar to the past trend? Remember, in finance, we use a concept called mean reversion. For example, PE ratios, they cannot be persistently too high or too low. They will come back to the normal range. That is called mean reversion. Mean reversion means there is a tendency to move back towards the average. This is a very important technical indicator. So, what will happen when there is a mean reversion? Mean reversion means there is a tendency to move towards its mean. It means if the value is too high, if the current value is above the mean, it will go down, right? So the value will decline if the value is above the mean. If the value is below the mean, it will increase, right? This is called mean reverting. And in time series, if there is a mean reverting, means the predicted value of X cannot go far away from the actual value of X. So very unique thing will happen is that your AR1 model, which was based on T minus 1, correct? But the value will go back to T. It cannot drift too much away from the past. So see here, the actual AR model was this, right? But when I say there is equality, equality means the mean reversion. Here you will see the X value is based on the past value of X itself. Very unique thing. Now, if this happens, this is called my mean reversion level. So what is a mean reversion level? I'll write down here what is a mean reversion level. And very interesting thing, mean reversion or mean reverting. Okay. In mean reversion level under the AR model, my X value will be B0 plus B1 related to X itself, current year X. Now, if this is the case, then what is my mean reverting level? So what is going to be my mean reverting level? If this is the outcome, then just see what I do now, guys. I will rearrange the formula. If you see this entire formula, right? In this case, here, if I further solve this, then I will take xt here and b1 I will take on the other side. So it will be minus b1 times xt equals to b0, correct? Now from this, what I will do is that I will try to solve this in a manner so that I get xt. Here my xt is common, so 1 minus b1 equals to b0. So my mean reverting level, which is xt, is equal to b0 over 1 minus b1. Yes, this is my mean reverting level. Okay, the unique thing is this. So here, if you will check what is your mean reverting level, your mean reverting level of x2 is b0 over 1 minus b1. Yes, this is my mean reverting level. What do I mean by that? That the value should be here if the value is higher than. So if the actual value is higher than the mean reverting, then the next value will be lower. But if the value is below, then the next value will be higher. Understood? So you have to come back to the mean reverting level. If your actual value is above, then it will decline, correct? If the actual value is below, then it will rise. This is called mean reverting level. What you need to remember is this formula of mean reverting level. I'll rewrite the formula here. I've written in the formula book although. So the mean reverting level is B0 over 1 minus B1. I just showed you the derivation of it. So how to use this? See here. calculate the mean reverting level for all this data. They have given us the information. I have the coefficients here, right? I need B0 and divide by 1 minus B1. So I will use the B0 divide by 1 minus B1. If I use that, I get a mean reverting level. This should be the outcome. Now, if the outcome is greater than this, then it will decline. If it is less than this, then it will increase. So based on this regression model, what did we conclude? This means that if the current level of manufacturing capacity is above the mean reverting level, then it is expected to fall, correct, in the next period. And if it is below, then it is expected to rise. This is what I need to know. Understood, everyone? Clear? Clear? Right? This is called mean reverting level, correct? Just, however, remember all covariant stationary time series have a finite mean reverting level. Means any of the model which is covariant stationary will have a mean reverting level possible. Okay, everyone? Clear, right? So they have said that any model which is covariant stationary will have a finite mean reverting level. It cannot be infinite. There will be a number out there. They've provided some additional information which you don't need, honestly. An AR1 time series will have a finite mean reverting level when the absolute value of the lag coefficient is less than 1. Absolute values means ignore the sign. So if you ignore the sign, whenever the B1 is below 1, here also if you see the B1 is below 1, ignoring the sign, then they are saying that the AR1 time series will have a finite mean reverting. This is extra information, you can skip it. Okay. Clear? This is what we concluded about the mean reverting level or mean revision. This is very evident, especially when you are forecasting something like, PE ratios and all, right? So this is where we completed the testing of the model using the t-test, and we just did mean reversion in time series. Now we are going to discuss what is in sample and out of sample forecast. Yes. Now, what is in sample forecast and out of the sample forecast? And based on that, we will discuss what is root mean squared error, number one thing, and what is the other concept which is related to instability of coefficients or called as non-stationary. These two things we will discuss in a moment, which will tell us some important information about the model. So this A and B, these are some important properties. But before that, let us discuss what is in sample and out of sample forecast. Okay. All of this is under the autoregressive model. So here, remember when first of all, we are going to get these values from software providers. So software providers will give us the different models. In the multiple regression model, when I had multiple options available from the software packages, we chose the one which had lower BIC as the fit model, right? So here also we have to choose between the different models, which model is best. Okay, so we will choose that. First of all, what is in sample forecast? Are within the range of data used to estimate the model for which time series is known as the sample of the test period. What is the difference here? In sample are within the range of data, and out of the sample are outside the sample period. That's the only difference. So in sample means we are testing within the range of data, and out of the sample when we are going outside the range. I'll explain you that, right? In sample forecast errors where T is the observation within the sample period. In other words, we are comparing what exactly? We are comparing how accurate our model is in forecasting actual data, correct? But what about out of the sample? In out of the sample also we are doing the same thing, but we compare how a model is in forecasting the variable y for a time period outside the period used to develop the model. Yes. See, for example, let's say I've used the last 50 years data, right? And I am doing the in sample forecast. So I am then actually something like I'm doing a back testing. What is backtesting here? So I am using the model to predict something from the past. So from the same 50-year sample, if I'm trying to predict, that's called in-sample forecast. But guys, you can tell me, when will you rely on the model? When the model will give you out of the sample forecast. So where the model will be able to accurately predict something from which I haven't derived the forecast. So not the past 50 years, but what if I want to predict the next 10 years? Then I will say the model is relevant. Okay, then the model has any sense in the real world. So see, what does it say? So out of sample forecasts are important because they provide a test whether the model accurately describes a time series and whether it has relevance. Relevance means, can the model be used to predict the future also? Okay, this is how I will analyze whether the model can be, help me in forecasting the future also. Past, no problem. That is like similar to like backtesting. Okay, we'll discuss about backtesting when we do portfolio. But what is most crucial is the out of the sample forecast. This has more relevance. However, analysts should be aware that most, of course, the most software packages that you will get, or the most researched that is published, that is in sample or out of sample. Most of the research is in sample forecast, that is based on the past. Understood this point? Correct. So which is better, in sample or out of the sample? Out of the sample. See, check here. When evaluating a time series model's real world ability to forecast, we would have the most confidence in a model with small error, right? We want the error, but which error, in sample or out of the sample, or residuals, everyone, error will always be there, but we want less. Which type of error in terms of real world scenario? Very easy. In sample forecast or out of the sample? Out of the sample forecast. Yes, that is where we want it to be less. And how do I know whether the out of sample forecast error is less? That is done using a calculation called root mean squared error, RMSE. So RMSE is the one that we use to compare the accuracy of autoregressive model in forecasting out of the sample values. So guys, here, when I want to test the AR models, when I want to test the AR model, out of the sample accuracy test, whenever I want to compare the accuracy of AR model, so whenever I want to compare accuracy of AR model, and in which test, not in out of the sample, not in the sample. So we remember here we had in sample forecast and out of the sample forecast. What is more reliable? We have out of the sample forecast, which is more reliable. So whenever I want to compare the accuracy of AR in forecasting out of sample, out of sample value, whenever I want to do this, then we use a test called RMSE, root mean square error. Okay, root mean square error, which is called RMSE. Okay, remember this error, we want always, the lower the error, better it is. Lower the error, better it is. So we'll discuss this. First of all, we want this to be lower. So I'll discuss the lower is better. Okay. Now we'll just discuss some component about it, but again, you do not have to memorize it. For example, a researcher may have two AR model between AR1 and AR2. Which one should I use? Of course, I will choose the one which has lower error. Okay, to determine which model is accurate, we calculate RMSE. They've used the information of how the RMSE is calculated. You don't need to do. Just remember, the lower the RMSE is more reliable, but lower RMSE in sample, no, lower RMSE out of the sample, and both may not be the same. Okay, so they have given us, imagine that we have 60-month historical data. We estimate both models over the first 36 months to determine how the model will produce the forecast for the next 24 months. Okay, so we are using out of the sample data, using the actual values of the last 24 months, we are trying to predict the future 24 months. So then we will calculate RMSE for each. Don't worry how the RMSE is calculated. Just remember, lower RMSE for out of the sample data, the lower it is, the better it is. We'll have lower forecast error and we'll have better predictive value. So therefore, I've written here the lower is better. Lower better for which one? Out of the sample. Okay, I will write down that addition here for out of the sample values or out of the sample data. Whenever the RMS is lower is better. So suppose if you are doing the testing for various model, always remember the one which has lower error is better, isn't it? Correct, correct. However, along with RMSE, we will also check one more thing, that is we will examine the stability of regression coefficients. When I say stability means we will test whether the coefficients are unstable or non-stationary. So along with RMSE, we will also test whether the coefficient are are instable or instability. Instability is also termed as instability is also termed as, if you check here, is non-stationarity. You need to know both instability, or I use the word non-stationarity. This is more common word in the statistical world. So we are going to use this also. We are going to test whether the coefficients are unstable or not. Okay, so what is that? Financial and economic time series inherently exhibit some form of instability or non-stationarity. Means, guys, the values are not the same. When I talk about mean reversion, no, what if the situations have drastically changed? There is a dynamic change in the market. So because financial and economic conditions, sorry, why have I reached here? Because financial and economic conditions are dynamic, the estimated coefficients in one period may be very different from the other period, right? So if I use a very short period and if I use a very long period, both are an issue. How? So model estimated with a shorter time series are more stable because there's not too much of a volatility, correct? But we know larger sample is better, right? But those with longer sample time series, why? Because longer sample period increases the chance of economic process being changed. This is what we call as, remember I told you in the past, it is also called regime change. So if you use a longer time series, there is a high chance of volatility. Things might have completely changed. So should I use a very short period or a very long period? They are saying there's a trade-off. What is a trade-off? Trade-off between increased statistical reliability when you use longer time. Remember, larger sample is better. But if you use more time period, then there is problem of stability. Stability is there if there's a shorter time period. Okay. So the primary concern when selecting a time series is the underlying economic process. If the economic process has changed, you cannot take a longer period. You'll have to use a shorter period. So we need to ask the questions. Have there been a regulatory change? Have there been a substantial change in the economic policy of the government? What if the economic policy was before very strict and now it is very liberal? So if the economic policies have drastically changed, you will see the impact different. So then I should not include the whole time period. I should divide the time period into both parts, before the change and after the change. So if there has been a dramatic change in the economic environment, then you cannot take a longer period. So they are saying if the answer is yes, then the historical data may not be reliable. Merely examining the significance of autocorrelation will not indicate whether the model is valid. We also need to examine whether the data is covariant stationary. So instability of coefficient means we need to check whether there has been a substantial change in the regulation or in the economy. If there is a change, then the historical data might not be reliable. So what is the conclusion under this? We need to check whether if we use a shorter time period, if we use a shorter time period or a longer time period. Longer time period is good but shorter time period will have less instability. Shorter time period, less instability. It's good, correct? But the longer time period is good from the statistical point of view. So longer time period, right? They increase the stability, correct? So see here, they said it's a trade-off. There's a trade-off between increased statistical reliability when longer time period. So longer time period has increased statistical reliability because we know large sample is better, correct? But if there is a regime change, then a shorter time period is preferable. Okay, so shorter time period is preferable if there is a, I use this term regime change. They use a term that is a change in the economy or change in the policy. So if there is a regime change, then a shorter time period is more reliable. Understood, everyone? Correct? We already did questions based on this. Just to show you what exactly we have covered till now. So till now, we have also tested the accuracy of the AR model using RMSE, which should be lower, and non-stationarity, where a shorter period is preferable. This is where we complete the discussion of trend analysis, linear and log linear model, and auto-regressive model. Very high chance of auto-regressive model being asked in the exam. Got it? Everyone understood till this point? So, what all we have done till now, let us understand that. First of all, we've done the trend analysis, where we did the linear and the log linear model, and then we moved on to AR models or autoregressive models. Under the autoregressive models, we have covered the very important property of covariance stationary. Covariance stationary, this is what we are going to discuss in a moment. What exactly is covariance stationary? And based on that, the future analysis will happen. Okay, so let me walk you through what exactly we've done till now and what is covariance stationary, as well as mean reverting level. Mean reverting level, if you note here, mean reversion. These two concepts are going to be very crucial when we go ahead. Okay, so before we start, what is random walk and unit roots? Let us quickly take a snap about what exactly we covered till now. Okay, so first, we did start time series model where we are trying to understand the trend or the pattern. So we did with the linear trend model, everyone visible, right? Linear trend model where y equals to b0 plus b1 t based on some time. And then we did the log linear model. We understood when to use which model, what is the reason behind using a linear and log linear model. This is where we completed the comparison of both the models, and then we tested the models. Yes, we tested the model, which model is best, correct? We tested the model using the DW test, correct? And then we also understood the limitations of the trend model. Of course, it is very much related to the assumptions of multiple regression, correct? And one of the assumption was, which was being violated, is the autocorrelation or serial correlation, right? This was one of the most important assumptions of multiple regression, which is perhaps to be tested when you're using models with time series. Got it? After that, we did realize that what is AR model, autoregressive model. These are models where the dependent variable is dependent on its own self, or I should say rather than on its own lagged value. So XT is dependent on XT's previous year value, correct? XT is dependent on XT minus 1, right? This are auto-regressive model. Very, very, very important. And this is where came the most important thing, which will be very important for us in the future analysis as to what is covariance stationary. Everyone with me on this? Covariance stationary? Covariance stationary, this is the most important thing because here we need to understand that if the model is covariance stationary, only then we use it. Covariance stationary, what exactly it means? It needs three conditions to be satisfied, which we discussed, that the constant and finite expected value and variance, and the same with covariance, constant and finite. correct? These properties or these conditions, when they are met, only then we can use the model. Otherwise, the model is unreliable. We cannot use the model, right? These three conditions, very, very, very essential, which we will need. AR can be ARP model, means one lag or two lag or multiple lag variables, but they're still called AR models, correct? And again, to test the AR model or to test the coefficients, right? We were worried about which issue with AR model. We are worried about the which property being violated or which assumptions being violated here about the multiple regression, about autocorrelation. So we did a core autocorrelation test, everyone in the class, right. Autocorrelation and testing the fitness of the model. This is where we compare the formula, where we detected the autocorrelation. Remember autocorrelation, for that we did the DW test, Durbin-Watson test, right? And the number was 2. If it is equal to 2, there is no autocorrelation. If it is not equal to 2, then there is autocorrelation. Autocorrelation means the model is not fit. So if we rejected the null, then we concluded that there is an autocorrelation and the model is not fit. This is what we did, right? Correct? In this, remember the autocorrelation test, we used a t-test or test statistic also, correct, to test the coefficients, right? And here we wanted to test whether the coefficients are significant or not, right? Here the null was that the coefficient is insignificant and we wanted to reject the null. If that is the case, then the coefficients are not equal to 0. Then we can say the coefficients are significant or worth using in the model. Okay. And after that, went on ahead with, after doing the autoregressive test, we understood the second most important thing that will be needed now is the mean reverting level. What is mean reverting level? Mean reversion is the tendency to move back towards the mean. So if the value is above the mean, it will fall down. If the value is below the mean, it will raise up. So here in this case, that mean reverting level, which we rearranged and derived, which is the most crucial thing, the mean reverting level is B0 over 1 minus B1. B0 is the intercept divided by 1 minus B1. Remember, this is very, very, very crucial. We'll require this as well. Covariance stationary conditions and mean reversion level. These two things are going to be very essential now when we go ahead, right? Now, in the market, there are various AR models available, right? So which model is better? We did the in-sample forecast and out-sample forecast, right? And along with that, to find that which model is more suitable, we calculated the error, that is RMSE, root mean squared error. So the model which has the lowest root mean squared error, that is the model we selected. And along with that, we also discussed about the issue of instability or non-stationary. When the stationary, covariance stationary things are not met, that is non-stationary. So for non-stationary, the duration should not be too high. Otherwise, there will be a lot of volatility. Here, I give you all a word which is not there in your notes. It's called regime change. Whenever the economic conditions have drastically changed, then we cannot take the whole period together. We need to split the period. That is what we discussed till this period, where we were discussing about the instability of coefficients, or called as non-stationary property, right? Correct. So in your index, if you note, this is where we are. We've done the trend analysis and we've discussed about the AR models, right? Now, out of these, as I mentioned, two things are very crucial: that what is covariance stationary, the three conditions, and what is mean reverting level. Okay. So let us understand a new concept called random walk and random walk with a drift. Drift. Very interesting. Okay. First of all, what is random walk? Random walk is a time series, correct, process where the predicted value of the series, predicted value, why? Correct. In one period is equal to the value of the series in the previous period. So yes, the value in one period is equal to value in the previous period, plus something called as a random error term. Yes. So what is the value in one period is equal to the value in the previous period plus some error. Okay. So here, imagine that, let's say, what is going to be the interest rates in the upcoming period is equal to interest rate in the previous period plus some random error, right? So this type of a model is called the random walk, a time series with random walk. Okay. Now, time series that follows a simple random walk process is described as, see this, xt is equal to xt minus 1, the previous year value, okay, plus the error. So it's random walk, which is the value is based on the previous year plus one thing that is called the error, everyone. So where the best forecast of xt is xt minus 1. Yes, so xt is dependent, or I can say the value of xt is based on the previous value, that is historical value xt minus 1. Correct? Now, one very interesting thing here, what will you notice in this case? If you see here, xt value is equal to the previous year value itself and plus error. So if there was no error, we would say the value of xt is equal to xt minus 1. For example, what will be the interest rate today is equal to interest rate last year plus some error. Okay. If there is error is 0, if the error is 0, check here. If the error is 0, the value, expected value is equal to the past value, right? So the expected value of each error term is 0. The errors are constant. See, these are the properties of covariance stationary, right? And the errors, the correlation between the error is 0, means there is no serial correlation. These three conditions are perhaps the same conditions that you saw about covariance stationary, right? What are the covariance stationary conditions? Same condition that you will see here. This perhaps means that the value of xt is equal to the previous value plus something, that is error. Now, what will you notice before I go ahead with what is random walk with a drift? Now, until now, you might not understand what exactly is going on. So, to systematically understand, remember, random walk is similar to the regression equation, but one thing that I did not include in that equation is that the B0 under this equation was 0. Everyone. B0 was equal to 0. If you say B0 is equal to 0, then the value of xt is equal to just the value of xt minus 1. Correct? But when I say random walk with a drift, you will notice there comes something that along with the rest of the thing, you will now have B0 also and B1 equals to 1. So in the previous case, there was no B0, there was no B1, but now you will see B0 does exist. Everyone, B0 also exists. So B0 is the drift and B1 equals to 1. What is B1? B1 is the slope. It's equal to 1. If B1 is equal to 1, guys, notice in this equation, xt is equal to xt minus 1, correct? Same, like random walk. Plus that B0. That B0 is drift. So when I say random walk, means xt equals to xt minus 1. So here also I can say this is the case when B1 equals to 1. Everyone, right? So when I say random walk, B1 is equal to 1, but B0 was not existing. But when I say random walk with drift, here I do have B0. B1 is of course 1. That means xt is equal to xt minus 1, right? The previous year value. However, there is something extra that is called the drift. So if a time series follows a random walk with a drift, the intercept term is not equal to 0, which was the case previously. Now it is not equals to 0, right? This is an addition to random error term. The time series is expected to increase or decrease by a constant amount each period. Yes. So xt, see if the B0 was 0, xt will be equal to xt minus 1 only, right? But now since there is B0 and assume the B0 is plus 1. So whatever is the previous year value plus something, plus something. So it will keep on increasing. If it is negative, minus, it will keep on decreasing. So that B0 is the drift. It is going to give you the trend, whether it will increase or decrease. Otherwise, the current value and the previous value will be same. Okay. So what is most important in random walk? Just a random walk, your xt equals to xt minus 1 plus error. In random walk with drift, it is B0 also. So We will write down in our formula here, random walk. Everyone, and you can also write down with me, random walk without drift. And then I will say random walk with drift. Okay, what is the equation? In both the case, when we say xt, everyone, here I will say xt is b0 plus b1 xt minus 1, correct? And plus error, plus error. But guys, in the previous case, when I said random walk, two things which we assumed. What are the two things? That is the B0 was equal to 0 and B1 equals to 1. Due to this, the xt got translated into simply xt minus 1 plus error. Are you with me, everyone? Understood this? Please give me a thumbs up if you have. Again, I will write here B0 plus B1 xt minus 1 plus error. But in this case, my B0 does exist. So there's a drift. And of course, B1 is equal to 1. So now my xt, everyone in the class, it will have B0. B0 will be existing. Plus, I can say xt minus 1 plus error. So now I cannot say that my value will be same. The value might increase or decrease. Everyone with me on this? Check, check, check. Can you please confirm? Right? Okay. Now, along with this, hello everyone. Yes, you can confirm. Along with this, you know what is the mean reverting level, everyone in the class? The mean reverting level is, we all know what is the mean reverting level. It is B0 over 1 minus B1. B0 over 1 minus B1. Now see, very, very interesting thing, everyone in the class. When there was random walk, I will write random walk without drift and with drift. Can you tell me what will be the mean reverting level? Random walk without drift. We had B0 equals to 0 and B1 was equal to 1. Here B0 is not equal to 0 and B1 equals to 1. So can you tell me what will be the what will be the mean reverting level, everyone in the class here? Mean reverting level in both the cases. Here the mean reverting level, please notice this. In both the cases, here my mean reverting level, let's say B0 is 0 over 1 minus 1. You need to tell me what is the answer. And here, let's say B0 is some value, whatever value you choose. Let you choose any value. Okay, even you can choose 0, even you can choose anything like 0, non-zero. Let's any value that you use here, B0 divided by, again, if I say 1 minus 1 is 0. So here, everyone in the class, in the previous case, the value, if I put here B0, again, here also B0 and here also B0. Now you will say there is no difference, isn't it? Correct? Both the equation have same thing, right? But in the second equation, we don't have B0. In the second equation with drift, the B0 will not be equal to 0. Am I correct? Right? Okay. Now, guys, what is common under both? Random walk with drift or without drift? What is common under both is that under both the cases, it will be B0 over 0. B0 over 0. Am I correct? Yes. Now, guys, before we go ahead, let me tell you, any number divide by 0 or 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 I can say 0 divided by any number or 0 divided by any number. Have you ever tried this in your calculator? Which one is a finite and which one is a error? One of the number your calculator will give you error. Have you tried it? Or I'm sure by now you must have tried it already in your calculator. So if you take in your calculator, divide any number, let's say 1 divided by 0, you will get error, isn't it? Any number divided by 0, will result into error, error, error. Am I correct? Have you noticed this? Any number divided by 0 will translate into error. Are you getting this in your calculator? Please check any number. But guys, 0 divided by any number. 0 divided by 0 is also 0. No, 0 divided by 0 is error. 0 divided by any number but not 0. Or you can say, you can perhaps use 0 on the top. If you use 0 on the bottom, it will turn into error. But if you use 0 divided by any number, 0 divided by 5, 0 divided by 1, 0 divided by 2, if you use 0 divided by any finite number, then you will not get error. Have you tried it? Can you tell me what do you get? 0 divided by any number, please. Yes. 0, 0 divided by any number will result into 0. Now, why are we discussing this? Because of one very important property of covariance stationarity and mean reverting level, that the mean reverting level should be finite. There should be a finite mean reverting level. Now, the problem is whether you do random walk or whether you do random walk with drift, because your B0 mean reverting level is B0 over 1 minus B1, and under both, the issue is that B1 is equal to 1, B1 is equal to 1, and that creates a problem. Because B1 is equal to 1, everyone in the class, the answer will be any number divided by 0. And any number divided by 0 is not defined. Your calculator throws you an error. That means time series must have finite mean reverting level. Yes, it should have a finite mean reverting level. But in this case, it will not have a finite mean reverting level. If this is the case, can we use the equation, guys? No. Therefore, a random walk with or without drift is not covariance stationary. This concept of it not being covariance stationary is because that the B1 is equal to 1. This concept is called unit root. Unit root. Everyone in the class. What is this B1 equals to 1 issue called as? It is called unit root. And I know for a fact that for it to be covariance stationary, there should be a finite mean reverting level. Yes, neither random walk nor random walk with drift exhibits covariance stationarity. So in this equation, since even if my B0 can be finite, but since B1 is equal to 1, which is called as unit root, because of this, what happens is that the random walk with or without drift becomes covariant. Does it meet the property of covariance stationary? No, it does not. So therefore, it is not covariance stationary. This is the issue when you are using such a model where the value is dependent on the past. Are you with me, everyone? So whether the B0 is 0 or not equal to 0. First of all, it is 0 when it is 0 for a random walk without drift. With drift, it is not equal to 0. But B1 is equal to 1. That was common under both, and that resulted into covariance non-stationary. Understood, everyone with me? Why is this model not usable? Because it has the problem which is called unit root. Unit root. Now, unit root problem, due to this, should I not use this model? No, I can use this model. I can fix up this problem. Okay. But first, let us understand how do I test whether a model has unit root. Remember, when I say unit root, unit root means the B1 is equal to 1. That makes the model non-covariant stationary. So this problem where, what is the common problem here? The common problem that B1 is equal to 1 is called unit root. And unit root means the model is not covariant stationary. Everyone in the class. So whether I say random walk with or without drift, both are non or both do not meet the covariance stationary property. So both are not covariance stationary. So I will write here both are not covariance stationary, not covariance stationaries. I cannot use them. So why? Because of unit root. And what is unit root? Unit root is the issue where B1 equals to 1, and that is the outcome which we just discussed. So here, unit root creates a problem that it becomes not fine. We want finite. We want finite mean reverting level. It is not finite. This is not finite mean reverting level, not finite. This is what happens under random variable with or without covariance stationary. Unit root means it's not a finite way, it's not a finite mean reverting level. Your calculator throws you an error. So whenever B1 is equal to 1, we cannot use the random walk with or without drift. Now, the procedure is that, okay, so what do I do about it? First of all, for a time series that is not covariance stationary, the least square regression procedure that we use to estimate the AR model will not work. So, okay, ignore it. No, 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 no. We will use it. We will do what? We will transform the data. Yes. Now we are going to transform. We are going to transform the data so that we can use such model. The problem with the model is that it does not meet the property. So we'll fix it. Okay. So first of all, we are going to understand how to detect the problem, and then we will try to fix it up. Okay. So everyone in the class here, correct? So everyone, the series is not covariance stationary, which we saw. If the value of the lag coefficient is equal to 1, lag coefficient is equal to 1, which I just mentioned, where B1 equals to 1, which is called unit root problem. If this is the case, under this case, it is said to have a unit root and will follow a random walk process. So I can't use it. Yes, we understood. Since the time series follows a random walk is not covariance stationary, modeling such a time series AR model can lead to incorrect inferences. Yes, we already know that this is the problem, right? So what do I do? How do I first test it and then I fix it? So we are going to now understand this issue in two parts. First, we are going to test that whether the AR model has unit, the autoregressive model, the trend here, does it have a unit root problem? First, we'll detect that. And second, we will bring a solution to it. Yes. So there are two parts. First, we are going to test for unit root. I will write down here testing for the problem. Problem is whether you have unit root, correct? Once you have tested, then we need to fix it up. And when I say fix it up means we will transform the unit root data to covariance stationary. So we will do what, guys? We will transform the problem. What was the problem? The unit root, the unit root that we had, the B1 equals to 1, correct? That unit root data, we will transform and make it covariance stationary. Once you make it covariance stationary, guys, then you can use that model. So first we'll detect the problem, then we'll fix the problem. Understood? So we are going to do unit root testing for non-stationarity, or non-stationarity means it's not covariance stationarity. Okay. Here also, I will write down the same thing. We are first going to discuss how to test whether there is a problem of non-stationarity. So testing for non-stationarity. I know while you all are writing, you all might be wondering, where am I going to use this in real life? Where this is used by the ones who are going to create the model. Now, fortunately or unfortunately for us, we are just going to borrow the model and use it. Okay. In real life, we are not going to create a model. Correct. But yes, if you were data analyst, you probably would realize that what goes into creation of the model. Okay. So testing for non-stationarity we are going to do. Here, there are two ways of performing the test. One is we are going to run the AR model test, or simply we are going to run an AR model. So run an AR model. Okay, this is what we are going to do first thing. And second is what we are going to do is that we are going to perform a Dickey-Fuller test. So the second is Dickey-Fuller test, or simply said as DF test. These two things we are going to do, right? Let us understand that. Everyone, to determine whether the time series is covariant stationary, number one, we are going to run an AR model and examine for autocorrelation. So actually, we are going to do the autocorrelation test. So even though when I say we are going to run the AR model, we are going to test for autocorrelation. Test for autocorrelation. Now, if you remember, we already did the test for autocorrelation. Everyone in the class, if you notice here, test for autocorrelation where the null is whether the autocorrelation exists or does not exist. And we did a t-test where we did autocorrelation divided by the standard error, which is 1 over square root of t. Everyone, right? So I will write down the same thing. What happened there? We were testing null and alternate. The null is that whether the autocorrelation is equal to 0 and not equal to 0. Everyone. So yes, if the null was rejected, we said yes. If the null was rejected, I'll conclude. What was our conclusion, everyone? If the null is rejected, then we concluded that autocorrelation exists. This is the problem, and then we cannot use the model. Correct? This is what we did. Now, to do so, to test it whether there is autocorrelation or not, we did a test. Everyone in the class, let us see the test that we did. We did a test which was where we were doing the t-test and where the degree of freedom was t minus 2. Yes. And the test was autocorrelation. The test statistic was autocorrelation divided by standard error. And standard error was simply 1 over square root of t with degree of freedom t minus 2. I'm doing the same thing. This is what we calculated the test statistic. Of course, we'll compare with the values, critical value provided to us, right? This is what our test statistic was. This is the same test that we run. We run an AR model and test it for autocorrelation. If there is autocorrelation, it is not covariant stationary, it is non-stationarity, and we cannot run the model. Okay, of course, we are going to fix it. We are going to see a solution to this. But first, we wanted to understand whether there is covariant stationarity or not. Okay, so now see this here. In the first method, everyone, an AR model is estimated, okay, to test the significance of autocorrelation at various lags. Stationary process will usually have residual autocorrelation insignificantly different from 0 for all lags. Yes, means the autocorrelation should not exist. When they say insignificantly different from 0 means what do we want? We want the autocorrelation to be equal to 0. If it is equal to 0, we say it is covariant stationary, otherwise not. Understood? So, and that too not for one lag. If you are using multiple lag, t minus 1, t minus 2, t minus 3, then for all the lags, it should be covariant stationary. So 0 at all the lags or residual autocorrelation that decay to 0 as the number of lag increases. So our goal is that there should be no autocorrelation, and for that autocorrelation should be equal to 0. So we want no autocorrelation. This is what we want. We want if the AR is equal to 0 means there is no autocorrelation, and if that is the case, then we can use the model. Correct, everyone? Now, the second test which we are going to do is Dickey-Fuller test. This is a new test, Dickey-Fuller test. Everyone, under the Dickey-Fuller test, we are going to do what? We are going to transform the data, which is non-covariant stationary, into stationary. Now, remember what was the problem? The problem of unit root was that B1 was equal to 1, correct? Now, statistically, there is no test for proving whether B1 is equal to 1 or not equal to 1. Okay, so we cannot use a test where B1 is equal to 1 or not equal to 1. So here under the Dickey and Fuller created rather ingenious test for, very interesting test for unit root. Yes. What is that test? Guys, as I said, we cannot do B1 equals to 1 or B1 not equals to 1. That is statistically not possible, correct? Because probability cannot prove something or statistics cannot exactly prove something, right? So therefore, very interesting. What will happen is that we will convert the null and alternate into a very interesting thing. Please see this, where instead of saying b1 is equal to 1, we will translate b1 minus 1 is equal to 0, or b1 minus 1 is not equal to 0. Now everyone in the class, here, if the null is rejected, then I will conclude that b1 is not equal to 1. But if you fail to reject the null, guys, if you fail to reject the null, then the conclusion will be b1 minus 1 is equal to 0, or I can say b1 equals to 1, and that means that there is a problem of unit root, means covariance in station or non-stationarity. Understood this, everyone? So what happened in the Dickey-Fuller test? We converted the correlation test where we wanted to know whether b1 is equal to 1 or not, but we can't do that. So we converted, we transform. Yes, everyone. So what happened here? The Dickey-Fuller transformed the AR1 into a simple regression, and for that they did all this rearrangement and they subtracted xt minus 1 from both the sides. I'll explain you how did they arrive to this. But you need to understand that the model was translated from b1 equals to 1 or not to b1 minus 1 is equal to 0 or not equal to 0. This is how we translated. How did we do that? See, this was the normal model, correct? Right? This was a normal AR model. What we did is that we subtracted xt minus 1 on both the sides. Some mathematics they did here. So we subtracted xt minus 1 from both the sides. And then if you notice what happened, here x minus xt minus 1 means basically this is change in x. What is this change in x? From last year to this year, t minus 1 to t. What is the change in x? Is equal to, they just rearrange this equation where they got b1 as xt minus 1 as out, and then the model had b1 minus 1. This is what we tested in the model. From b1 equals to 1, we are now moving to b1 minus 1 is equal to 0 or not. This now satisfies a proper equation, a statistical property, and this is what we can test, right? Now see this. So rather than directly testing whether the original coefficient is different from 1 or not, which we cannot, right? The new transform coefficient b1 minus 1 is different from 0 or not is what we will do using a modified t-test. Of course, we don't need to know what exactly that test is, but a t-test, a modified t-test, if, and what I wanted, guys, if the b1 minus 1 is not significantly different from 0, means b1 minus 1 is equal to 0, that means we fail to reject the null. If we fail to reject the null, means b1 is equal to 1, and therefore it must have a problem of unit root. This is how we identify. Okay, I'll also write it here. Under the Dickey-Fuller test, what do we transform into? We transform, see guys, we transform our b1 equals to 1 into b1 minus 1 is equal to 0. So here what we did is that we transformed our model to the AR model, okay, by subtracting xt minus 1. So we transformed the model and we are going to conduct modified t-test. A modified t-test. Everyone in the class, we are going to do the modified t-test where the null and alternate, everyone, the null and alternate will be b1 minus 1 is equal to 0 or not equal to 0. But here, if I get this, so my conclusion it is fail to reject the null. If this is the case, that means b1 is equal to 1, and that is the problem. That means it is non-covariant stationary, or I can say that the model has unit root problem. Everyone, unit root problem means it is not covariant stationary. We cannot use it. So it is non-stationary. So this means it has a problem of unit root. Unit root is proven, and that means it is non-stationary. Non-stationary means I cannot use the model. So see here, very different. In the autocorrelation test, in the autocorrelation test, if again, what is the conclusion? That there is an autocorrelation and I can't use it. If I reject the null, everyone, means there is an autocorrelation. But here in the Dickey-Fuller test, if I fail to reject the null, that means there is a unit root problem. I'll repeat, in the autocorrelation test, if we rejected the null, null means there is no autocorrelation. But if we rejected it, means there is autocorrelation. In the Dickey-Fuller test, the null is b1 minus 1 is equal to 0. But if we fail to reject that, that means b1 is equal to 1. And that will become a unit root problem. That means we cannot use the model. Understood, everyone? Correct? So then our AR model, which is a trend model based on the past, we can't use it. Now, to fix this up, we are going to use the first differencing. Okay, first differencing, we'll understand what exactly it is. And again, we are going to use the test. We will first detect it and then we will resolve it. So what happens in a first differencing? Again, just remember here, we are going to transform, okay, the model. If we believe the time series is a random walk means it has a unit root. I'll rewrite here, unit root means b1 equals to 1. If that's the case, we can transform the data to covariance stationary. And how do we do that? Everyone, that process is called first differencing. So first differencing is where we transform the unit root to covariance stationary. Now, of course, you must be interested in how exactly this happens. So I'll directly show you the model. What happened here, everyone in the class? That your xt minus xt minus 1. Yes. What was our normal model? See, I'll show you the derivation of it. Okay. Remember, the initial model was xt is equal to b0 plus b1 xt minus 1 plus error. Correct? This was the model. Am I correct? Now, here, considering b0 was equal to 0 and our problem was that b1 was equal to 1, right? b1 was equal to 1. That is the problem. That's why it was covariance non-stationary. So if we now see the model, if we input these values, then this will be 0 plus 1 into xt minus 1 plus error. So basically, my xt will be equals to xt minus 1. Am I correct? Which is nothing but it's going to be equal to plus error. Now, guys, very interesting. Therefore, I can say xt minus 1 is nothing but error. Everyone in the class, this is what the conclusion will be, right? Okay, now we know that yes, this will be the conclusion. So the error is nothing but the change in x. When I say xt minus 1, that is nothing but that is the change in x from last year to this year. So see this, what happens, everyone? The first differencing process involves subtracting the value of the time series in immediately preceding period. Correct? From the current value of the time series. So from the current value xt, we subtract xt minus 1 to define a new independent variable y. Note, by taking the first difference of xt and xt minus 1. So what do you mean by first difference? First difference means taking xt and minus xt minus 1. The difference of this is called first difference. You model the change in the value of dependent variable. So this is how I get the change. Everyone. So what is my normal model? What do we do here? Y, which is the dependent variable, is nothing but equals to the change in the independent from last year to this year. Everyone, right? Why? Because we said b1 is equal to 1. So y is equal to nothing but y is equal to the change in x. For example, if I want to see what is the bond's value, well, the bond's value is dependent. Let's say, what is the bond's change in yield? It is not value, but bond's change in YTM is equal to change in X. X can be interest rate. Correct? So then stating Y in the form of AR model, see this. So therefore, my Y equals to this same model. Now, what has happened? Y is equal to B0 plus B1 of the previous year value, YT minus 1 plus error. So here, if you see here, eventually, what is Y? Y is nothing but the change in the value here, which is nothing but the error term. error term, or nothing but I can say the same thing. This is what the outcome of y will be. Now it might sound a bit complicated, but what has happened that whenever I'm going to predict a dependent value, its value is equal to nothing but the change in the value. So when B0 and B1 are 0, if you put up in this equation B0 and B1 both 0, then Y is nothing but the error. Remember, error is something, the unsystematic risk that the model is now going to give me beyond the model. What is going to be my return? That is error. Now, is it covariant stationary or not? Now, to understand this, remember when I say B1 and B0 both are 0, then my covariant stationary is B0 over 1 minus B1, which is 0 over 1 minus 0. Now, 0 over 1. If you do 0 divided by 1, you will still get 0, which is finite. But 1 over 0 is not finite. So, it does meet the property. Understood? Now, what exactly are we trying to do here? Or what am I supposed to do in exam? In exam, you just have to identify whether there is a unit root problem or not. And if yes, then we need to take a value of y based on the previous year value. I will show you both what is first differencing. So hold on, see what is the outcome, and then we will do question related to this as well. Okay. So see this. Suppose we decide to model the capacity utilization data that we just did. Okay, using an AR model, the results indicate capacity utilization time series probably contains a unit root. So that means it is not covariant stationary, right? So discuss how this time series can be transformed. Well, we can transform using the concept of first differencing. First differencing, what is first differencing? Yes, we just know the name, right? How is that done? Let us see, everyone. So here we've been given the same information. The first difference in the first differences of the original series are contained in the third column. So here the third column you will see the value of yt based on based on the previous year value, and then yt minus 1. Everyone just notice this yt, and then it is yt minus 1 year back. Okay, so please notice here the differences of the original series are contained in the third column, and one period lag values of first differences are presented in the fourth column. So in the fourth column, we went one period back. So this is the fourth column information, and this is the third column information. Got it, everyone? Now, what is the outcome of this? Based on this, what we do is that we calculate the first difference. Now, we don't have to do anything like this in exam. We just saw the difference. So here, when I look at the difference of yt, that is just the change in x. So if you do 82.4 minus 81.5, that will give you a value of 0.9. And if you do these changes, if you keep on doing these changes and then you do the lag changes, you will see the notice. You will notice it. This is how it appears. Now, after this transformation, it is appropriate to regress AR1 model. So now, once I have transformed the information into this format, this is called first differencing. Once you do this, then now you can use the model. So now what is going to be my conclusion? My model will translate yt equals to B0 plus B1 yt minus 1. Now, this is how we transform the model. Now, I don't know whether the model has been transformed, whether I can use it or not. I need to test it. Okay. So what are we going to do? The results for the first difference time series are presented. Okay. We are going to test it at 5% significance. Now, to test this, let us see here the model, and they will give you the output of the model. We will have to conclude whether I can use the model or not. So this is our AR model. Our AR model will eventually translate. I will write after doing this. What is the solution here? The solution is we are going to do the transforming. So first, before I make you all see the outcome, what are we going to do? We are going to transform. We've transformed the data, right? So we've transformed the non-covariance or covariance non-stationary data or the unit root data into covariance stationary. So we are going to first try. I'm first going to write. So solution to the problem of unit root. Solution to unit root. What is the solution? Well, we are going to transform transform, transform the unit root data to, covariance stationary, to covariance stationary. And how are we going to do that? Well, we are going to do that through a concept called first differencing. Yes, first differencing. This is the solution for unit root problem. Okay. Now, what is first differencing? Under this first differencing, the model gets transformed into the lag value. So here, my value of y, everyone, is dependent on b0 plus b1. Again, the value of y plus error. But guys, here, which value? I'm going to translate this into which value, everyone? Yt is based on yt minus 1. This is how we translated the model, right? This is the model that I can use. And under this model, why is this model covariance stationary? Well, it is covariance stationary because it does not have unit root. Okay. So this is going to be the solution to my unit root problem, is that we need to transform the non-covariance stationary data into the covariance stationary. So eventually our model will be this. Okay. Now, again, we need to first prove it, or we need to test it. So if we look at the R square, adjusted R square, standard error observation, here are the coefficients, and the lag coefficient is this. And we look at the p-value, everyone in the class. And I know the p-value, this p-value, if I reject the null, remember what was the null here? The null, I will write down the null and the alternate. Under my test, modified t-test, my null was b1 minus 1 equals to 0. b1 minus 1 is not equal to 0. Okay. So since my p-value, guys, here my p-value is how much? 1.48 percentage, correct? And they said test it at 5% significance. So p-value is below 5%, or I can say p is below the alpha. So my decision will be, everyone in the class, can you tell me, if the p is below alpha, we reject the null. We reject the null. And what is a null? A null is that b1 is minus 1 is equal to 0. We reject this. So we reject the null. If we reject the null as per our decision, so our conclusion is that b1 minus 1 is not equal to 0, or I can say b1 is not equal to, sorry, 1. This means the model now does not have a unit root problem. Understood, everyone? And therefore, I can say it is covariance stationary. Clear? Everyone? Understood? Now, after explaining the model, let me show you in the case study form how exactly all of this appears, so that we can perhaps utilize in our exam also, right? This is just understanding of the concept. How the concept is translated into exam information. Let me show you that. Okay. So this is what the model is. This is the information that they've given us. B0 equals to B1 RC T minus 1. Again, the same thing. Y, if you notice, let's say if I say this is Y, okay, this is equal to B0 plus B1 of Y T minus 1, isn't it? Correct? Plus the error, right? Everyone, it's the same thing. So this is, again, this is my AR model only. So if they say what type of time series model was used to produce the regression in the table, well, this is an AR model only. AR model, heteroskedasticity is arc model, which we haven't discussed here. We will discuss that later on. And trend model with a drift. No, this is not with a drift. Understood? Why? Because we are regressing this RCO, RC, or revolving credit study. So basically revolving credit outstanding. So we are regressing. Why is this AR model? Because you are regressing RCO, current value of RCO, on the lag value of RCO. That is, you are regressing RCOT based on RCOT minus 1. Whenever you are regressing on the lag value, it's an AR model, correct? Right? Right? Itself, you are regressing RC0 with RC0 itself, right? Okay, now the second one, we will see it in a moment, not now. Okay. Or can we do this? An approach that may work in case of modeling a time series. Yeah, oh, we can do the second one. Yes. Which approach may work in case of modeling a time series that has a unit root? What is the solution for a unit root model that you are familiar with? Yes, you can try, everyone. When there is a unit root issue, what should we do? How do we fix it, everyone? Using the first differencing approach. Now in exam, you need to just know the names to be precise. So not an arc, not a trend model. Trend model is not workable. Model the first difference of the time series. Yes, whenever there is a unit root problem, the solution is first differencing. Clear? Understood, everyone? Right? Okay. Now see, which of the following will always have a finite mean reverting level? What is finite mean reverting level, guys? Finite mean reverting level means B0 over 1 or B0 over 0. By the way, the original formula is mean reverting level is B0 divided by 1 minus B1. Now, guys, when will this be 1 and when will this be 0? If guys, my B1 is equals to 0, and here if my B1 is equal to 1, B1 equals to 1 is unit root problem. Am I correct? And any number divided by 0 is error. Am I correct? So, which of the following will always have a finite mean reverting level? Of course, finite mean reverting level is acceptable, right? The non-finite is not acceptable. So, yes, my answer should be very easy. Everyone in the class? A covariance stationary time series, right? Random walk with or without drift, none of them. Unit root, definitely not, because unit root means B1 equals to 1. That will result in error. So this has unit root issue. We cannot use this model. Clear? That's non-stationary. Which of the following statement is most accurate? A random walk process is non-stationary, has a finite mean reverting level, can be appropriately fit in as an AR model. Everyone in the class should answer this. Question number 4. A random walk process is a non-stationary random walk, guys, with or without drift. With or without drift. Both are non-stationary. Am I correct? Yes or no? Yes or no? Both are non-stationary. Easy. So see all of this information, the questions that they ask is very easy. A random walk process is non-stationary. Here, watch out. A random walk we discussed. This is what we discussed. Random walk and with or without drift, right? So here, if you notice here carefully, guys, a random walk with or without drift, both are non-covariant stationary because both have unit root problem which can be fixed using a first differencing concept. Understood? Which of the following is not correct about Dickey-Fuller unit root test for non-stationarity? Now, let me show you what is the Dickey-Fuller test, where the null is B1 minus 1 is equal to 0 and the alternate is B1 minus 1 is not equal to 0. So, before I go ahead with the question, when they say Dickey-Fuller test for testing the unit root problem, my null and my alternate, well, it transformed the equation, right? So, B1 minus 1 is equal to 0 or not equal to 0. Guys, when do I say that it's a unit root problem? It's a unit root problem when you reject the null or you fail to reject the null. Everyone, when you fail to reject the null, right? In that case, your B1 minus 1 is equal to 0 or B1 equals to 1. That means it has a unit root problem. Correct? This is what we understood. Am I correct? So let's see which of the following is not correct about the Dickey-Fuller test. Okay. The null hypothesis is that the time series has unit root. Yes or no, everyone? That's correct, right? The null is that it has unit root. If you accept the null, guys, if you accept the null means fail to reject the null. If you fail to reject the null, that means B1 is equal to 1 and that means it has unit root. So A is correct statement. We are looking for incorrect. Am I correct? Second, B. Hypothesis test is conducted using the critical values computed by Dickey-Fuller in place of conventional t-test. Yes, we are going to do the Dickey-Fuller test. No doubt about this. So of course it's C, but let's see why C is wrong. If the test statistic is significant, right? Significant means B1 minus 1 is not equal to 0 or 0. When I say test is significant, yes. If I say significant means, when I say significant means B1 minus 1 is not equal to 0, or I can say B1 is not equal to 1. If this is the situation, then it is not unit root. And if it is not unit root, I can say the model is covariance stationary. I can very much use the model. So if the test statistic is significant, our conclusion will be we reject the null. And guys, we conclude that the time series is non-stationary. No, we rather conclude that time series is stationary. Because when I say it is significant means we reject the null. Whenever I say significance means we reject the null. Are you with me, everyone? Clear. Understood? This is all about the AR model, where we are going to do the AR model based on the lag value. And this is where this is called random walk with or without drift, and fixing up for the problem of non-covariant stationary, which is called unit root. Unit root happens when B1 is equal to 1. In this case, the value is equal to the past value, the lag value. So we need to fix up. First, we need to test whether the model, whether the coefficients are, whether the problem with the coefficient is that whether they are covariant stationary or not. We test it. If it is, using both the test, the normal autocorrelation test or using the Dickey-Fuller test, when we do the test, when our outcome proves that there is unit root, we can't use it. If it is not unit root, then we can use it. Clear? Understood? Very interesting thing. Got it? Yes. And we did a question related to that as well. So coming back to our broader index so that you are in sync, what did we do? We completed random walk with and without drift, unit root testing, the two tests that we did, correct, for non-stationarity, right? That is the Dickey-Fuller test, and run model is auto regression test basically. And the solution to that was first difference same. That was the solution where you use the lag value, where the mean reverting level then becomes finite. Okay, right? Now we are going to detect seasonality. Yes. Seasonality. Basically, what seasonality means, there are many businesses where the regression models are based on some, trend or season, monthly sales data of a retailer, quarterly sales data of a steel company. Business are cyclical. So due to this, there is some trend with regards to this seasonality pattern, which we will now understand whether the model has seasonality into it. Well, if it is seasonality, then there will be a problem because it will violate some of our assumptions. How do we correct for that seasonality and how do we use it? Because, so see, all of the models that we use, the AR models, we detect some of the assumptions are violated. We fix those assumptions by adjusting something into the model, and then we use the model for our future analysis. This is where we are going to detect seasonality, one of the very important things. Okay, let's start with understanding seasonality. So if there is a pattern which is repeated year on year from last quarter to this quarter, let's say last December or monthly also, it can be quarterly or monthly. So something that happened in last December is repeating this December also because of the season. That model is called the model which has seasonality. Now remember, seasonality is, violating the assumption of regression. Yes, I'll tell you how and how do we fix it. So first of all, what is seasonality? Seasonality in a time series, if a pattern is repeated from year on year, it's called seasonality, right? For example, they've given monthly sales of a retailer. Given that the sales data normally vary according to the time, we might see that pattern. And what is that pattern? That we expect the month sales, the current month sales, to be related to the same, say, to be related to the sales of the same month last year, 1 year back. So xt minus 12. Yes, if it's monthly, if it is quarterly, the current month will be related to the last quarter or last same quarter of last year. Okay. So when seasonality is present, remember that the time series is non-covariant stationary, right? Or non-stationary. When seasonality is present, modeling the associated time series would be misspecified unless we fix it up. And how do we fix it up? Unless the AR model incorporates the effects of seasonality. Yes. So if you use a model which has seasonality, first of all, we will detect the seasonality, right? If there is a seasonality, yes, then we will have to change the model. We'll have to input something into the model or add something into the model so that we can use the model. Okay. So let us understand that. So first of all, if you will notice here, because it's the sales, it's a number, right? Therefore, we use a log. Are you with me? Right? Because we have sales. Remember the log linear trend model? So log of xt current year is, if you see here, it is log of xt minus 1 last period, right? Okay. You are interested in predicting the occupancy level for a resort hotel chain and have obtained the chain's quarterly occupancy level. But here, current year quarter, you are trying to relate it with the previous quarter. However, the fact may be that, let's say my currently I'm in Q4. So it might not be related to Q3, but it might be related to Q4 of last year. Okay. Yes. Now, for most recent 40 quarters means 10 years data. You decide to model the quarterly occupancy time series using AR1 model. Okay. So we went back only one, we had only one lag, right? Now, before we use this model, we need to detect for seasonality. So they have asked us determine whether the seasonality exists or not. So number one thing is what we are going to do. We are going to detect the seasonality, right? Now, for that, I'm going to write here what is seasonality and how do we detect for seasonality. Yes. So seasonality in AR model, this happens when there is a pattern. Okay. And there is a pattern in the sales, right? So if what is my normal model when there is a pattern which is expected to repeat? So seasonality is basically when there is a seasonality is when there is a pattern which is expected to repeat or pattern which is repeated. In this case, first we are going to understand how to detect seasonality. Okay. Once we detect it, then we'll try to fix it up. Okay. So first we'll detect and then we will add something into the model to use it. So detecting the seasonality, there is a t-test and there is a hypothesis. So which test are we going to use? We will see that. And interesting thing is, what is the hypothesis? So the hypothesis, basically, I have to find out what is going to be the null and the null and the alternate, right? And which of the one will tell me whether there is seasonality or no seasonality, right? Well, some of the things are going to be similar what you have already done. So here in this model, we have been given the output of the regression, correct? So this is my AR1 model based on one lag variable, right? Observations I have n minus 1, 40 minus 1 is 39. Okay. R square, remember the R square is 0.79. Okay. We'll utilize that R square later on. Okay. Now I have the coefficients lag 1, okay, and the t-stat. T-stat you will notice is 3.256, okay, quite high, right? For the coefficient. And this is my value of coefficient. Residual lags, autocorrelation of the residuals. Residual lag 1, 2, 3, and 4. And you will see some outlier there. It's the fourth, which is an outlier, or which I can say is highly significant, isn't it? Correct? So amongst the lags, you will see lag 4 is highly significant. Now, what do I mean by this? We will have to understand this. Okay. So the bottom part of the table contains the residual autocorrelations. Yes, the autocorrelation test, which we did in the past, right? The autocorrelation, whether it is equal to zero or not equal to zero. Yes. So which test are we going to do? The autocorrelation test. Autocorrelation test, which we already know. Here we are going to conclude whether the autocorrelation is equal to zero or not equal to zero, everyone. And if it is not equal to zero, if it is equal to zero, means autocorrelation does not exist. So if this is the outcome, we will say that there is no autocorrelation. No autocorrelation means no seasonality. So I will conclude whether the seasonality exists or not. If the null, we do fail to reject the null, I will write down here properly. If we fail to reject the null, so seasonality, whether it exists, yes. If we fail to reject the null, if we fail to reject the null, so seasonality does exist or not exist, everyone. If we fail to reject the null, I'll repeat, means autocorrelation is equal to zero. So I will say there is no seasonality, correct? But this, if I reject the null, I will write down here, if I reject the null, and the null was that there is autocorrelation is equal to zero. So if I reject the null means autocorrelation is not equal to zero. And when I say autocorrelation is not equal to zero, that means there is seasonality. Okay. So I want no seasonality, but I will get to know if there is seasonality when the null is rejected. So the issue is this. Autocorrelation should be zero. There should be no autocorrelation. But if it is, then there is if it is zero, no seasonality. But if it is not equal to zero, it is significant. That means there is seasonality. Okay, now let us see that in the information of the question as well. So everyone here, the first 4 lags of the time, what stands out relatively large autocorrelation and T statistic for the fourth lag with 39 observation. Okay, there are 37 degree of freedom at significance 5. They have given us the critical value 2.026. Now we will see this critical value is 2.206. This is my critical value. My test statistic is 5.4446. So my conclusion is going to be reject the null. Am I correct? Correct. Yes or no? My conclusion is going to be reject the null. Everyone in the class. And when I say reject the null, what was my null and what was my alternative? My null and my alternative. My null was that the autocorrelation is equal to zero or not equal to zero. So I rejected the null. So when I reject the null, I accept the alternate, means autocorrelation is not equal to zero, means there is autocorrelation, or I can say the seasonality exists. Autocorrelation means there is a correlation from the previous year, so there is a seasonality. Yes. So the T statistic indicate that none of the first 3 lags autocorrelation is significantly different from zero. So yes, in the first 3 case, I didn't find their value to be greater than 2.026 or less than the -1, right? So therefore, in these 3 cases, we detected no seasonality because we rejected, or we did what? Sorry, we failed to reject the null. So in this case, we failed to reject the null. So we had no seasonality, correct? But not in the case of fourth one. However, the T statistic for fourth, which means we must reject the null that the lag for autocorrelation is zero. So yes, we got to know amongst all the lags, we did the lag autocorrelation. And for the fourth one, we realized that it is not equal to zero. So yes, instead of just saying autocorrelation, I will use the word lag autocorrelation. Okay, for any of the lags. Here we got the fourth lag significant, means we rejected the null. That means there is seasonality. Everyone, right. Correct. Now, once there is a seasonality, we cannot use the model because it is, again, as I said, covariance non-stationary, right? So conclude that the seasonality is present, and thus we conclude that the model is misspecified, unreliable for forecasting we need to include the seasonality. This is going to be the solution. So what do I need to do? I need to include the seasonality to correctly specify. So until now we detected the seasonality here, everyone. Now what we are going to do, we are going to fix the seasonality, or we are going to correct the seasonality. So how do I go to step number 2? That is correcting the seasonality. Correcting for seasonality, right? Now, while I'm doing all this thing, in your background, it's going, hey, you know what? It's nowhere related to level 1. My level 2 CFA quants, it's completely out of the box. Yes, it is. Okay. The students were initially surprised because they didn't see linear regression also in level 1. So many students complained that what is this all of a sudden not related to what is linear regression at all. So therefore they added up linear regression very recently. So students have some idea, but it doesn't help a lot. Okay. So yes, how are we going to correct for seasonality? Well, the way to correct the seasonality or adjusting is when we add into the model one more lag independent variable. So what are we going to do here? Our model, see, our model will translate. When I say correcting for seasonality, we realize that the Q4 was significant. So if you see, what is the solution here? To adjust for seasonality in AR model, and additional lag of the dependent variable is also added to the original model. So how do we correct it? We add additional lag, we add an extra lag of the dependent variable of the y. Means if you already had, y dependent on Q1, now we add Q4 also, which is called a seasonal lag. Everyone, see here, that seasonal lag is lag 4, which is called the seasonal lag. Additional lag, which is called the seasonal lag. So now a model will translate, see, from log B0 plus B1 this. Now an extra thing is added into the model, which is B2 log of X2 to XT minus 4 1 year back. So this is my seasonal lag which is being added. So then my model translates, I will write down here. Initially my model, my lag of the value, we were looking at only the previous quarter value, right? So lag of value of xt was equal to b0 plus b1. We use the lag of xt minus 1, correct? This was our original model. But then how did we fix it up? We added a seasonal lag, which is plus b2 times x log because it's revenue, log of xt minus 4. This is quarterly, so minus 4. If it was monthly, I would say t minus 12, correct? Plus the error term. So everything else is the same. The only thing that was added, an additional seasonal lag was added. This is called my seasonal lag. That was added. So now I can use the model. First, I detected that there is a seasonal lag and we added something into the model. Okay. Now, guys, by doing so, it's still an AR model only. Okay. See here. So what we did, we added the model. Now it results in AR1 model incorporating a seasonal lag. So you cannot say it's AR2, it's AR1 only, but with the seasonal lag. Because many people think, oh, this has now become AR2 model. No, 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 no. Let me show you that what is written here. Everyone. By testing the correlation, okay, it appears that the occupancy, okay, that is fine. Now to adjust this, you see here, sorry. Note that this specification that the inclusion of a seasonal lag does not mean that it has become AR2 model. It's still an AR1 model only. So by adding a seasonal lag, the model is still AR1 model. It does not become AR2. It doesn't mean you see normally AR2 is T minus 1, T minus 2, right? This is not called AR2 model. This is T minus 1 and T minus 4. It's called a seasonal lag. Understood the difference? Everyone? Clear? AR1 is T minus 1. But when you take previous T also, T minus 2, T minus 3, T minus 4, normally we say it is what? AR2, AR3, AR4 or ARP till P. But this is not AR2. This is AR1 with a seasonal lag. That's the difference here. Okay, everyone? So now you will see this is called AR model with the seasonal lag. Everyone. So this is not the AR2, but it is a seasonal lag. Correct? Now, if you also notice what has happened by doing this, the R square has improved. Check it. Previously, in the same model, R square was 79. Now the R square has improved to 94, which they have discussed. If you see here, by adding the fourth lag residual, what also notable, see the second point. Also notable is that the result has improved the R square to 94 from the previous 73. This indicates that by incorporating the seasonal lag, the model has now become more correct, right? Because we want the R square to increase, isn't it? Correct, 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 correct. Yes. So now by looking the same information, we will see the test statistic has been provided. And now looking at the autocorrelation of the residuals, everyone in the class, look at now, none of them are statistically significant. Initially, Q4 was, right? Now you will see here, everyone in the class, notice that in the bottom of the table, the fourth lag residual autocorrelation has dropped substantially and is in fact no longer statistically significant. When they say no statistically significant, it means the lag for autocorrelation is perhaps zero. The lag for autocorrelation not equal to zero, that was the alternate. So the null, so when I say insignificant, or basically I conclude that the autocorrelation does not exist, right? So we say it has dropped and it's no longer significant, means we fail to reject the null. When we fail to reject the null, when we fail to reject the null, this is what is called fail to reject the null. That means there is no more seasonality. So the seasonality has been fixed. Now we can use the AR model. Clear? So the solution is that you add a seasonal lag. Now see in exam what type of question will appear. Okay. So based on the regression, okay, we've been given the occupancy level over the past year. Forecast the level of the hotel company for the first quarter of 2023. So Q1 2023. I need, right? Sorry. Q1 2023. So I need to go one quarter back. That must be the AR model, and then Q1 of 2022. So I need Q1 2022 and I am going to hotel forecast the level of hotel occupancy for the first quarter of 2023. So what I'll do is that I'll go one quarter back. So that is the last quarter of 2022. So this is going to be my T minus 1 and this is going to be my T minus 4. I'll add the lag. So now the model is log natural. What is my intercept? Yes, these are my intercept and slopes. Everyone, intercept 0.0085. And I have the slopes been given to me for lag 1 and lag 4. So this is going to be my lag 1. This is going to be my lag 4. So carefully, I will put my lag 1.2598 into 600,000 and lag 4 into 250,000. This is the value that I'll put. And then when I find the value with the intercept, you will get this amount. Plus, just check it, please, everyone. Are you getting the same value by putting all the numbers? I'm sure you will get the same values. So you can also try the same thing, everyone. 600,000 log natural into 98 store 1. Then you will do 250,000 log natural into 0.921 store 2 plus 0.005. Yes, you'll get 13.3102 to be precise, or 13.3103, which is log of y. But if I want to find y, that is the occupancy level, you'll have to do exponential of both. So you will press second ln. When you do second ln, you will get 60337. I'm getting 603,334, which is fine because we are using the exact value. So you might get something different 603342. I got 342. Are you getting the same or you're getting different? Or maybe I must have done something wrong. 60, I got 603342, which is closer. Okay, 60337. Did you get this or you got 603342? Yes, please tell me. If you use exactly 13.3102 second ln, you'll get this value. This is going to be the forecasted level of the hotel occupancy. This is how I inculcated the seasonal lag. Understood, everyone? Clear? What is the one step that we did here, guys? We just final value that we got here, we need to do the exponential of both so that we get the y, right? So we press second ln. When you press second ln, that is exponential. Got it? Now, let us do a question related to seasonal lag, everyone. So here is the model regression result for monthly cash flow studies done. Intercept with lag 1 and lag 12. So these are monthly, right? So we do lag 12. Okay. P value is 56.12. P value is it? Now, even if you take 5% significance, and they told us any significance, whatever significance you take, 5, 10, or 1, P is greater than alpha. So we fail to reject the null. Am I correct? We don't reject the null. And that means that there is seasonality or no seasonality. Can you tell me? Everyone, it's not significant, right? So there is seasonality. Why? Because then I will conclude that the autocorrelation is 0 or not equal to 0. We fail to reject the null. Yes, we fail to reject the null. Very interesting. When we fail to reject the null, the p-value should be low. The p-value is high. So when I will say this, we fail to reject the null. Remember, it's better you always write it if you get confused. So autocorrelation, the lag autocorrelation is equal to 0. When I say fail to reject the null, means there is no autocorrelation, means there is no seasonality. No seasonality. Understood, everyone? When I fail to reject the null. Correct? Okay, so we can very much use the mod. Now, the first thing they said, the number of observation in the time series used to estimate the model. Everyone, now number of observation, how do I find this? Everyone in the class, how do I find this? Remember the autocorrelation test? I will help you understand what was the autocorrelation test, everyone. The autocorrelation test statistics was the autocorrelation divided by standard error, and standard error was equal to 1 over square root of t. Everyone with me? 1 over square root of t. That is what my standard deviation, standard error was. Correct. So here, to find the number of observation, I know for a fact that the standard error was 1 over square root of t. Now, why am I doing this? Because if you carefully notice here, in this, they've given me the standard error of the lag term. And they've asked me the other thing. So I've got the standard error of the lag term, and we already concluded that there's no seasonality. So 0.0632, that is what my standard error is, 0.0632. And I don't know what is the sample here, right? So what are we going to do? We are going to rearrange this. So therefore, I will say 1 over this is going to be square root of t. So square root of t will be 1 over 0.0632. Everyone in the class, 0.0632, inverse it, and since it's square root there, if it comes on this side, it becomes square. So just press x square, you will get 250.36. 250.36. This is what you will get. We just had to reverse everything. 250, everyone got it? Yes. Now guys, they are asking, everyone got it, right? Yes. Based on the information, what type of model was used? Is it AR1, 2, or 12? Guys, remember the seasonal lag model is, everyone, yes. Before I go ahead, it is AR1 model only. We cannot say it is AR2 model. We say it is AR1 with a seasonal lag. We say it is AR1 only, but we say it correctly. It is AR1 with seasonal lag. Seasonal lag. Understood, everyone? We don't say it is AR2. Okay. Right? Clear? Next. At 5% significance, does the information indicate presence of seasonality? First of all, did we get seasonality? Check, 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 check. We concluded that there is no seasonality, right? Everyone in the class? No, we don't see seasonality. The answer should be A. No, because the lag 12 autocorrelation of residual is not significant. Not significant. Why? Because the lag 4, or sorry, in this case, lag 12 autocorrelation is equal to 0, insignificant. Therefore, there is no seasonality, correct? Because we fail to reject the null. Am I correct? We fail to reject the null looking at the p value. Clear, everyone? Right? Okay, so there's no problem of seasonality here. Now, everyone, a time series model that uses quarterly data exhibits seasonality. If the fourth autocorrelation of the error term, yes, you can now try this. If the fourth correlation, lag 4 autocorrelation is 0 or not equal to 0, guys, under which case we can say that there is a seasonality. There is a seasonality when we, hello, when we say we reject the null. When we reject the null, everyone in the class. So when it is significantly different from 0, yes or no, everyone? What should be your answer? When the fourth autocorrelation of the error, that is lag 4 autocorrelation, it is 0, means no seasonality. It is not equal to 0, means there is seasonality. Everyone in the class understood why A is the answer? Yes or no? If it is 0, that means no seasonality, because then the autocorrelation is 0. Clear? Yes. Next, in the autoregressive time series model, which we just saw, seasonality may be corrected. How do we correct the seasonality? By adding the seasonal lag. Easy, isn't it? So by excluding no, by transforming the time series into first differencing, no, that is what we do for random walk with the problem of unit root. Correct? Not here. Here we add an additional variable that reflects the appropriate lag. Easy, easy, add. And the last one, which is pretty much easier, which of the following AR model is most appropriate for a time series with annual seasonality using quarterly observation? Guys, annual seasonality. First of all, it is not A because the intercept does not exist in A. So I'll not take A because there's no B0 there. So the race is between B and C. Yes, annual seasonality using quarterly observation. So all the observations are quarterly. So I should take 1 quarter back and same quarter last year. Same quarter last year, not month. Annual seasonality with quarterly lag means same quarter last year. Okay, see the confusion. So should I take this B or C? Everyone, B or C? We should take everyone in the class B or C, B or C, B or C. Same quarter last year, same quarter last year. So B1 xt minus 1 is correct, not xt minus 4. B1 xt minus 1 and same quarter last year. I should take this. So B is the answer. Everyone understood? This is the seasonal lag. This is my seasonal lag. Clear? Right? These type of questions they ask. Right? Now, coming back to the point again, what all we have covered, everyone in the class. So see here, we covered now the concept of seasonality. We detected whether the seasonality exists or not by running the autocorrelation test for the lag. We corrected by adding the seasonal lag, and we forecasted the model where we predicted the future revenue or occupancy rate or any number. Okay. Clear, everyone? Right? Till this point, yes, anyone, any questions? Right? Right? Yes. Everyone clear? So we've done till now trend analysis, linear, log linear models. We use the auto-regressive models. That's what actually we are doing. We are using the AR model, but some of the AR models have seasonal lag. The AR models have, in it, we need to test the AR models, whether they meet the properties of covariance stationarity or not, random walk with drift, without drift. Okay, all of these we are testing and then we are using the model because it violates the property of covariance stationarity. Okay, right? Why? Because the value is dependent on the past. So there is this problem. We detect the problem by doing the tests. We detect whether there is a seasonality or there is autocorrelation or not. All of this we detect and then we bring some solution. We fix those problems. Clear? Right? Okay. Now, what is that one assumption that you realized has been violated? Remember the assumptions of the multiple regression model. I'll have to walk you through these assumptions. So let me go through the previous topic where we focused on those critical assumptions and the violation of these assumptions, especially the heteroskedasticity, conditional heteroskedasticity, where the residual variance are related to the independent, means the error is related to the independent, the conditional heteroskedasticity, which we use the Brosh-Pagan test to detect it. Okay. Now, it resulted in type 1 error and therefore we got we were not very much the coefficients were not reliable. That is what we came up with, right? So the biggest problem was, everyone in the class, the heteroskedasticity, and that violated the assumption. Now those four assumptions, everyone, I'll just walk you through those. Actually, there were not four, there were many assumptions, but the assumption related to the error, which was the most crucial, the three assumptions in the center. Of course, the first is not a problem. The second, residuals are normally distributed. Okay. The variance of the error term is constant. This is what we wanted to understand, that the variance of the error, it needs to be constant. It need not change. Okay. So we are actually now going to do ARC model, ARC, AR model for with conditional heteroskedasticity. Now, before I make you understand what is ARC model, we need to understand what is conditional heteroskedasticity. And here, the assumption number 34234, residuals are normally distributed. The variance of the error term has to be constant, and the residual for one observation is not correlated with the other. So, guys, looking at that, when we went on to understand the conditional heteroskedasticity or heteroskedasticity, it was basically violation of which assumption, everyone in the class? When we got the conditional heteroskedasticity, it was the violation of that assumption number 3, where we wanted the errors to be constant. But what if the error increases or decreases in value, right? Then there is a problem of heteroskedasticity. Error being constant is called homoskedasticity, right? So just giving you all a reference here, what is the problem of conditional heteroskedasticity? And whenever an AR model has conditional heteroskedasticity, of course, we cannot use the model, right? So how to fix it and how to use it? That is what we do, right? So now we are examining a time series model, that is the AR model, with heteroskedasticity. And when I say which heteroskedasticity is the problem, conditional heteroskedasticity. So ARCH stands for basically ARC model. It is auto-regression, right? Or auto-regressive model with CH, conditional heteroskedasticity. So such an AR model exists if the variance of the residual in one period is dependent on the variance in the previous period. So here the model is going to talk about the variance. Yes, if you will notice, the ARC model looks like this, where the variance of one period is dependent on the variance of the previous period. This is not homoskedasticity. This is heteroskedasticity, conditional. Yes. When this condition exists, the standard errors of the regression coefficient in the AR model and hypothesis tests are invalid. We can't use it because it's violating the assumption number 3. Correct? So how do we use this model and how do we fix up it? Okay. So first of all, it means that the error of one term are related with the error of the previous term. Okay. And here the coefficient A1 will become crucial. Yes. So what are we going to do? We want this A1 to be 0 or not equal to 0. That's what we are going to test. The coefficients, the null and the alternate, everyone in the class. Right? This is what we are going to test in a moment. So an arc model is used to test for autoregressive conditional heteroskedasticity. So first of all, now what are we going to do? We are going to do the arc model. And in that arc model, what are we supposed to do? Everyone, what is ARCH? ARCH basically when a autoregressive model has conditional heteroskedasticity. So if AR model has conditional heteroskedasticity, I'm just writing in short form, then we cannot use the model. So first of all, we'll have to do the same thing. We'll have to detect whether the model has arc or not, whether the model has conditional heteroskedasticity or not. So we are going to detect for heteroskedasticity, or I would say conditional heteroskedasticity. Conditional heteroskedasticity. This is what we are going to detect into the model. And how do we detect, everyone? That is the arc model. So to detect whether the model has conditional heteroskedasticity or not, we use a arc1 model. So to do so, we are going to use a arc1 model. What is an arc1 model? I will just describe in a moment. So instead of just saying AR model, AR1 model, we will use ARCH1 model. Okay, now let me show you that. So an ARC model is used to test for autoregressive conditional heteroskedasticity, everyone. So under this model, what are we supposed to do? Here, within the ARC framework, the time series is one for which the variance in one period is dependent on the variance in another. So to test this, the squared residual from estimate time series model are regressed on the first lag. So you're going to regress the error with the first lag, one lag, right? Now, this is where, if you remember, for conditional heteroskedasticity, we use the Brosh-Pagan test, the BP test, correct? Now, are we going to use the BP test here? Not really. We are not going to use a BP test. We have a different test here. So we are testing where A0 is constant and mu, here mu of t is the error term. Okay. So here the error cannot be said as E only because we are actually trying to see whether the errors are correlated or not. Okay. So if the coefficient A1 is statistically significantly different from 0, first of all, if it is 0, if A1 is equal to 0, guys, then error is not dependent on the previous one, right? But guys, if it is statistically different from 0, means I will reject the null. So if I reject the null, everyone, means it is not equal to 0. So if it is statistically significant from 0, the time series is arc1. Yes. So then there is an arc1, because then it is not 0. If it is not 0, means there is an arc. So the time series is arc. It has arc. So how do I detect it? I detect it if based on the null and alternate. So the null and alternate, first of all, I'll write the model. What is the model? First, conditional heteroskedasticity. So what is the model? My model will be translated into error, and we say variance of error. Okay. So we are predicting the variance of error in T is equal to B0. Instead of B0, we here use the word A0 plus A1 into, now check out this, error of T minus 1, and instead of error saying error again, we use the different term here, mu. Okay. Now here the entire entire way to detect, or the solution to detect whether the model has arc 1 or not, is testing the A1. So if the A1 is equal to 0 or not equal to 0, if it is 0, then these two things will not be correlated, right? So then this and this entire term will be 0. So the problem is that if it is 0, no problem. There is no arc. But if it is not equal to 0, this will happen when we reject the null. So here if I say I will reject the null, if I reject the null, that means the model has arc. The time series model has arc. So my conclusion will be that the time series model is is having arc. Time series model has arc, or autoregression with conditional heteroskedasticity. So I can't use the model until I fix it. Correct, everyone? We can't use the model, right? So if a time series model has been determined to contain R, we already said that there is heteroskedasticity and therefore we can't use the model. So once I detected it, I can't use it. So what is the solution? The solution is what we are talking about. Now, first we detected. So now solution. So the first part was detecting whether there is arc. Detecting the arc, correct? Auto regression with conditional heteroskedasticity. And now we are trying to bring a solution to it, right? So they are saying such a generalized least square must be used in order to develop a predicted model. Now, what do they exactly mean by this? So here I will just show you exactly what do they mean by this. Now, if you look at this, so predicting the variance, if a time series has arc errors, use an arc model to predict the variance of the residuals in the future. So we are going to use this arc model to first predict the error. For example, if the data arc1 pattern, the arc1 model can be used in order to predict the variance of the residual in period t plus 1. So then I will use the arc model, and here it might sound very weird, but the solution here is that if you detect it, then you will first predict the error. So we will forecast or predict the error for t plus 1 based on the previous. So here now once I know that there is an arc in it, so then I will predict the variance of the error or t plus 1, which will be based on the variance will be based on the, see, my next variance here. If you see, the variance of the next period is based on error, everyone. So see here, conclusion, everyone. For example, if the data exhibits arc1 pattern, arc1 model can be used to predict the variance of the residual in t plus 1. So t plus 1 is dependent on the previous. So here they have used, this is based on the t plus 1 is dependent on t plus 2 is dependent on t plus 1. So then my model is a0 plus everything is predicted. Okay. A1 into, we will use error of t. Similarly, t plus 2 will be based on t plus 1. Okay, now again, do I have to remember this? No, you don't have to remember this. You just have to see and apply. See, I'll tell you what exactly you need to do. So they have said here that they've got the AR1 model here. Okay, where is the information? TR regress on the square, that is all fine. Determine whether the results indicate autoregressive conditional heteroskedasticity. So first, we have to detect. If yes, then calculate the predicted variance of the error in the next period, and the current period value is given. So for next period, current period value is given. So first of all, I'll have to detect, they've given me any model which is based on the variance of the error. That means it's an arc model. Okay. So I have lag 1, that is my A1. I need to check whether the A1 is significantly equal to 0. It is significant or not, means whether it is equal to 0 or not. So I need to use the hypothesis. Everyone in the class, that A1 is equal to 0 or not equal to 0, right? Here I will see the p-value is way below 1%. So my conclusion will be reject the null. And when I reject the null, means I will accept this. That means A1 is not equal to 0. Not equal to 0 means it has conditional heteroskedasticity. Everyone, because it is significant. Am I correct? So since the p-value is on the coefficient is less, very low, then we conclude that the time series is arc1. As such, the variance of the error term in the next period. Now, guys, very easy. First, you just need to understand that yes, there is arc1. Simply try to predict the future variance. So if I want to find, if I want to predict, they said the variance of the next period variance is dependent on A0 constant, and I will times A1, multiply A1 with the current period error that they've given me. Simple, no brainer here. If you do this, you get to know that what is this? This is the error in the next period. This is what the error will be in the next period. So this model is used to predict the error in the next period. Got it? That's the only way we are going to do. Here they said if the coefficient is equal to 0, had we got it equal to 0 means there was no arc in it, right? So the variance is constant. If A1 is, so I will write here, if the A1 was equal to 0, then the variance was supposed to be constant, means I can say there was no heteroskedasticity. In this case, suppose if that would be the case, there was no heteroskedasticity, or I can say no conditional heteroskedasticity. Correct? No arc. But if it is greater than or less than 1, then there is a conditional heteroskedasticity. Clear? Right? Now, based on what we discussed, how the exam questions will look like, very easy. They are not going to ask you to do a lot of calculation. They're perhaps going to, actually, they're just going to judge whether you know what the model is used for, to be honest enough. So, see here. Question number 2. Which of the following indicates a presence of arc in the time series model? The autocorrelation of the AR terms are 0 at all lags. See if it is 0. 0 means no autocorrelation, no arc. If it is not equal to 0, yes. So remember, null is that A1 equals to 0. The alternate is not equal to 0. If it is not equal to 0 means there is a relationship. So then it is arc. So if it is not equal to 0, then we said that there is a conditional heteroskedasticity. So the presence of arc means the autocorrelation are 0. No, the variance of the current error depends on the variance of the lag, isn't it? And the error term shows significant serial correlation at lag 1. Yes, everyone answer B or C? B or C? Everyone? Yes, the answer is B. That means the variance of current error is dependent on the previous one. Then we say there is R, conditional heteroskedasticity. Clear? Everyone? Till this point? Right? This is all they are going to ask you about arc model. Remember, arc model is for the variance, where the variance of the current period is dependent on the previous period, and we detect by checking the coefficients whether they are significant or not. If yes, then we use the arc model to predict the variance of the error. That's it. That's all what you need to know. Correct, everyone? Right? Okay. Now, finally, we are going to understand that when we use a time series model, we have two variables here, X and Y. X is the independent and Y is the dependent. Correct? So any time series model, everyone in the class, occasionally an analyst will run a regression with two time series. Two time series, one for Y, another for X. So they've given an example of, let's say, a CAPM model or a single index model where Y equals to B0 plus B1 X. The stock is dependent on the market. Y is stock, X is market. So here they are saying the Y and X, there are two variables, that since there are two variables, there can be two time series. Both can have a time series model, either of both which could be subject to non-stationarity. So we have to test for Y also. We have to test for X also, whether they are stationary or not. Okay. To test whether the two time series have unit roots. Unit roots means their B1 is equal to 1. The analyst first runs the DF test, differencing, the Dickey-Fuller test, right? with 5 possible results. When you do the Dickey-Fuller test, they are saying there can be 5 outcomes. Very, very interesting. First, both time series, that is X and Y, are covariant stationary. Is this a problem or not a problem? Amongst the 5 outcomes, if both are, the X and Y both are covariant stationary, is this desirable or not desirable? I would say this is desirable. Desirable means, guys, see here. In scenario 1, the analyst can use the linear regression. Desirable means you can use the linear regression. Everyone. The coefficients should be statistically reliable. Yes. But if one of the variable, whether dependent or independent, if one of them is covariant stationary, in this case, we will conclude that we cannot use the model. So even though the first one is desirable, the first condition is desirable. The second, when either of the coefficient, whether X or Y, when they are non-stationary, because one of the dependent variable or independent variable is non-stationary, then we say this condition is not desirable. We cannot use the model in this case. So see here, in scenario 1, the analyst can use the linear regression, and in scenario 2 and 3, they will be not reliable. So we can't use the linear regression. Everyone understood? So both X and Y should be covariant stationary, not only one, both should be covariant stationary. Sorry. Clear, everyone? Check, check, check. Okay. But there is one more solution to this, which is going to be very interesting, and that is what we are going to discuss. So this is the problem when we were discussing, this is the problem of unit root. Okay. When the two time series might have unit root. So this is the problem if the time series has unit root, either of them, then this is the outcome. But now look at the fourth and the fifth, for which we'll have to understand this concept called co-integration. Neither time series is covariant stationary, neither X nor Y, and the two time series are not co-integrated or they are co-integrated. What is the meaning of co-integrated? First, we'll understand that, but focus on they are co-integrated. If they are co-integrated, even before we read what is co-integration, I will say then it is desirable. But if they are not, then it is not desirable. So therefore, it is important to understand what is co-integration. Okay. See, X and Y. Remember, stock is dependent on the market. Okay. So what is co-integration? It means that the two time series are economically linked. So when I say the word co-integration means they are economically linked. There is some link between the X and Y. For example, if I'm predicting Y, that is the bond's price, it is dependent on market rates or interest rate, right? So there is some economic relation, even though statistically they might not fix up, but there is some economic relationship, right? Related to some macro variables or some trend, right? If the two time series are co-integrated, the error term from regressing one on the other is covariant stationary and the t-tests are reliable. Yes. So they are saying if there is an economic relationship, that means that they are co-integrated, then the model is reliable. Then you can use the model. So therefore, even though both of them individually are covariance, are not covariant stationary, but if they are economically related, then you can use the model. Clear? Right? So they are saying whether the linear regression can be used in scenario 4 or 5 depends whether they are co-integrated. This means that scenario 5 will produce reliable estimates, but not 4 because it's not co-integrated. So how do I do this? So to test whether the time series are co-integrated, we regress one variable on the other by following the model. They've used a simple model. We just regress, and what we conclude whether they are co-integrated or not. For this, we used a different test. It is called DFEG test. So the residuals are tested for a unit root using the Dickey-Fuller test with critical values calculated by Engel and Graner. Don't have to remember, just remember DFEG test. If the test gets rejected, everyone in the class, if we reject the test, what is the null and alternative? I'm writing here the null and the alternate. The null is that the B1 is equal to, remember the B1 is equal to 0 or not equal to 0. So suppose if I say if the null is rejected, if I'm going to reject the null, means their relationship is not 0. There is an economic relationship. So when I reject the null, means there is economic relationship. So which is called they are co-integrated. This will happen when I reject the null. So there is no random relation. There is an economic relationship. Clear, everyone? So see, if the test rejects the null hypothesis of a unit root, we say the error terms by the two time series are covariant stationary and the two series are co-integrated. Co-integrated means they have some economic relationship, right? So here I'm going to write, how do I test for co-integration? So co-integration means whether they are integrated, economically linked or not. So co-integration, what does it mean? It means that X and Y are economically integrated. That means whether the two time series, when I say two time series means X and Y, whether they are economically integrated or not. That is what we are testing. Economically integrated. And therefore, what do I do? We compare their errors, okay? Or we are trying to understand whether the relationship between them is 0 or not. So which test do we use? So we detect using, they used a word called Dickey-Fuller EG test. You don't need to memorize the name, just for your reference. Okay. So we are going to use DGEF test, where our conclusion will be, as I said, the null and the alternate. The null B1 is equal to 0, B1 is not equal to 0. I want to reject the null. We want to reject the null. If I reject the null, the alternate is accepted. So we will reject the null. When I say the reject the null, means they are co-integrated. Everyone understood? Means they are co-integrated. So we can very much use the model. Check here. So the critical values are tested by, the residuals are tested for unit root. So this is testing, detect, or I can say testing the residuals for unit root. Unit root means whether they are non-stationary or not. That's what we were testing using the Dickey-Fuller EG test. Okay, in exam, you don't have to memorize all this thing, right? Just you need to understand that the null, if it is rejected, means they are co-integrated, then I can use it. So see this matrix very, very crucial. Dependent variable, independent variable, dependent variable y, independent variable x. Now guys, if they both are covariant stationary, only then the model is desirable. So see, are they covariant stationary? Covariant stationary, yes. If they both are, only then the model is reliable. I can use it. Correct? But if either of them are not covariant stationary, then I can't use it. I can only use it if they are economically integrated or called co-integrated. Yes, if the two are co-integrated. So even though they are non-stationary, I can use it if they are co-integrated. Co-integrated means their residuals are not equal to 0. There is significance. Clear? Everyone understood this point? Everyone, right? Very important. This has high chances of being just tested. They might put something related to this. Let us see if we have a question. Yes. Linear regression. Yes, third question we can try, everyone. The linear regression is least appropriate for modeling the relationship between two time series when neither series has unit root. So if they have unit root, we can't use it. So they are asking least appropriate to use. No, when they don't have unit root, we can use it, right? So that's not the answer. When one of the time series has unit root, means covariant stationary. we can't use it. Correct? Yes. Both have unit root, means both are covariance, not covariance stationary, but they are co-integrated. So can I use or not? First one, I can use the model. Third one, since they are co-integrated, I can use, but in B1, I cannot use. Understood everyone? Why B is the answer? Please just confirm me on the chat box. Do you agree? That they unit root problem means they are not covariance stationary. I can't use it when even one of them is not covariance stationary. But if they are not covariance stationary, however, they are economically integrated, co-integrated, then I can use it. So in first case and last case, I can use it, but they are asking when you can't use it. That is when either of them are not covariance stationary. Clear, everyone? Right? Got it? Yes. Now we are going to be at the end of the topic. So where are we? We are at the end of the topic. So I'll just tell you the summary. What we have done is that we have understood the arc model, tested for conditional heteroskedasticity. Using that arc model, we predicted the variance. And finally, for non-stationarity or co-integration, we tested whether when can we use the model, because we have two time series here, X and Y. So at least they should be co-integrated. If not covariance stationary, they should be at least co-integrated. Then you can use the model. Clear, right? Wow. All those who say cons is easy in level 1, yes, but level 2 is level 10. Level 2 is not level 2. Level 2 is level 10. You know, I'm sure your head must be spinning by now. But see, before I go ahead, I wanted to say something about why in detail I'm doing everything. I'll probably say it after the end of the session. Don't worry. But just wanted to say that, the problem with CFA Institute is level 1 is here, level 2 and level 3 should be here, right? So level 1 is here, level 2 is here, all the way here till level 10. And then level 3 is not that difficult. So somehow the CFA Institute need to realize that level 1, 2, 3 means it should be in stages. Level 2 is way difficult than level 3. Level 3 is actually very easy to crack because the syllabus is also less. So I sometimes when I teach all the levels, I wonder why is level 2 so time consuming, so difficult than level 3? It should actually be the other way, right? But surprising. Okay, it's very vast. However, there is a big surprise that I actually passed level 1 and level 2 in first attempt. Level 3, I took 3 attempts, 3 years. So much so that I was about to give up. Not because level 3 is very tough. In fact, I was working in the same job profile of private wealth management, but only because I did not give time. In my 14, 15 years of career, I can tell you that there's a very less correlation about your knowledge and you passing CFA level 1 exam. No, no, no. It's not because of your knowledge that you failed or passed the CFA exam. It's about the discipline. Trust me, it's completely about the discipline. I have students who have no idea of what is this or how financial markets work, who are chemical engineers in oil and gas. They have no idea about how the financial markets work. Many of them have never traded in the financial market, but they have managed to pass level 1, 2, 3 with me. And that is just because of focusing on one thing, finishing the syllabus. Overthinking kills. Actually, the fact is that overthinking kills. Those who think too much, they miss out the opportunity. Those who just focus on the syllabus, pass. See, passing requires different skill, knowledge requires different skill. That's why many students, have this, oh, level 2 is not so much of a story, knowledge, market knowledge. It requires a different skill to pass. For knowledge, level 1. For knowledge, level 3. Level 2 is purely technical skills. You don't have time to deviate. You don't have time to drift. Understood? You are so much into the system, completing the syllabus, you have no time to think what is the practical aspect, what is the relevance in the market. That much time you don't have. Many people who overthink in level 2, they never give the exam. So based on my experience, I've realized the first thing is that we need to complete the syllabus, give the exam, pass the exam, and then you have enough time to discuss rest of the things. Got it? Yes. Now, what are we going to do? We are going to do the summary of everything that we've studied into the model. And that's why I've prepared the index in these types of, cases. Now, there are these steps, 8 steps in which they have summarized the entire topic. Very interesting. Okay. So determine the appropriate time series to analyze the investment problem. This is where we are going to discuss that in real life, we are going to use regression model for sure. We are going to predict the expected returns of stock, bond, various aspects. It's impossible that you're in the world of equity and debt investments and you don't use the regression model. Fortunately for us, we have many software providers which give us this model. So we don't have to do the technical aspect, but you need to know how it is done. Okay. So see, just give you a very stupid analogy. I know you all might laugh at this, but see, if I'm just going to use the fan, I don't want to know how the electricity is transferred. Okay. But if I'm going to be an analyst, understanding the efficiency of the fan, understanding, I'm going to be into the repair of it, then I need to know the mechanism of how it is worked. Same way, if you're just an investor, you don't need to get into the detail of this too much. But if you are a buy side analyst, if you are the one who's analyzing in depth about the equities, about the valuations, then you need to be like a mechanic or be like a guy who's going to repair and fix it. So then you'll have to go one step ahead. You'll have to understand how the electricity is transferred, how the mechanism of the fan works. So then you need to understand how the models are created. However, if you tell me that, Kunal, I'm not going to be into the valuation or forecasting or data analysis, then don't worry. Then you don't have to go into detail of this model in practical life. Okay. So here, to determine which model is best suited for our needs, these are 8 steps. Okay. Number one, first you need to ask what is the goal, okay, or the objective, because we saw various models, right? Trend, where we discussed linear and log linear, right? So are you attempting to model the relationship of a variable to other, means the past? This is where we use AR models, isn't it? So then we can use the AR models in this case, but they are saying, are you trying to model the variable over time? This is where we use the time series or trend model. I can say here we use the trend models, isn't it? Clear? So depending on what you're trying to look out, accordingly, you will use the model. Number one, easy, right? Okay. Second, if you have decided on a time series analysis, okay, whichever model you use, linear model or log linear model, right? Then plot the values over the time and look for characteristic that would indicate non-stationarity, those 3 properties, right? Because if it is non-stationary, then we can't use the model, right? Such as non-constant variance, heteroskedasticity, non-constant mean, or seasonality or structural change. Yes, seasonality and structural change. So basically 4 aspects they've told us to fix, to understand before you use the model blindly, right? Conditional heteroskedasticity, non-constant mean should be constant, right? Third, seasonality, then you'll have to add a seasonal lag, or structural change means the economy has drastically changed. Remember the regime change? So we need to check for all this. Also, so structural change they've described in detail. What do you mean by structural change? As I said, when the data, let's say the time period has huge economic change. So if that is the case, then they are saying there are 2 or more distinct patterns. You have to run 2 different models, one incorporating the data before and after the date. So let's say if there is a big policy decision, so you will have to run 2 different models. You'll have to plot the data before and after the date, after the shifting has happened. You'll have to split it. This is called how to inculcate the structural. This is how to, you will have to adjust. So they are saying before, let's say a decision was made, you will have to use different means. You'll have to divide the data in 2 parts. If the time series has shifted significantly, and if you use a single time series, then it will produce unreliable results. So you can't use a single time series if there is a structural change. Correct? Same way, we will detect for seasonality. As I said, seasonality, when there is a pattern, right? If there is a pattern, you will add a seasonal lag. Correct? So if there is no seasonality, however, then you can use the model easily. So you can then have to decide whether it's upward or downward, means it's a linear or if it's a log linear. If there's no seasonality, Go ahead. It's a trend model. You can use linear or log linear. You can decide. Next, run the trend analysis, compute the residuals, and test for serial correlation. Serial correlation or autocorrelation, you use the DW test. Okay, Durbin-Watson test. Correct, everyone? What was the Durbin-Watson test? Everyone check out for auto-regression. We use the Durbin-Watson test. Everyone, the AR model. Here, the autocorrelation test. And we use the Durbin-Watson test. Where is my Durbin-Watson test? Everyone? Yes, here. For the trend analysis, we use the Durbin-Watson test where we detected whether there is correlation or not. If the null is rejected, there is no autocorrelation. If it is if the null is rejected, there is an autocorrelation. If we fail to reject, that means there is no autocorrelation. So we detected the correlation under the trend model. If you detect no serial correlation, okay, green signal, go ahead and use the model. However, if you detect, then you can't use the trend model. You'll have to use the AR model. So yes, the trend model, this is what they are talking about, the trend model. Okay. So trend models, guys, I can use the trend models if there is everyone, no autocorrelation. Correct? But if there is autocorrelation, then I'll have to use the AR models. Everyone. So check out these models. If the data has serial correlation, everyone, then the data for stationarity before running an AR model, we need to recheck that. Okay. So in this case, if it is not stationary, treat the data in the AR model as follows. If it is linear, then in that case, they are saying use the first difference of the data. So see here, if there is an we are using AR model, in the AR model, we are going to test for autocorrelation. Everyone, if there is an autocorrelation, then we need to look out for the aspect where we are going to do what, guys? We are going to use the first differencing. First differencing is used to fix up the problem of unit root. Everyone, first differencing is what we use to detect. We use the for fixing the problem of unit root. Remember, first differencing is when do we use to fix the problem of unit root. Unit root is when b1 was equal to 1, correct? If the data has exponential trend, use the natural log. If there is a structural shift in the data, run two separate models. We already discussed. If there's a seasonal component, then add a seasonal lag, isn't it? This you will do when there is no problem with the data. But if there is a unit root problem, then we do first differencing. So when we do first differencing, then you can use the model. Okay. If the series is covariance stationary, run AR1 model and test for serial correlation and seasonality, which we already did. If there is no remaining serial correlation, then you can use the model. However, if you detect serial correlation, this is after the first differencing. If you detect the serial correlation, that means there is a seasonal lag. So first you use the AR model, okay, where you detected whether there is a seasonal lag or not. You detected the problem of unit root, covariance stationarity, right? But after that, after doing, and if there was a problem, you fixed it up by doing the first differencing, correct? This is what you did in this case. However, even after first differencing, there is a problem, means then we have a seasonal lag. That means we have a seasonal lag. So they are saying if no serial correlation remains, okay, you can use the model. But if you still detect serial correlation, then there is a seasonal lag and the solution is incorporate a lag value. So we use the Q4 of the same, we use the quarter of the same period last year, or, we use the month of the same period last year. So Q, you will see if, the T plus, what do we say? T plus 4 for quarterly or T plus 12 for monthly. That is what we add, correct? Finally, we tested for heteroskedasticity, that is arc model, right? Here, remember the mean reverting level we discussed, right? Of unit root means the mean reverting level, where anything divided by 0, 1 divided by 0 will be error. That happens when the B1 is equal to 1. Okay. Testing for arc, which we just did, regress the square of the residuals on the lagged value if they are significantly different from 0. So here we concluded in this case, A1 is equal to 0 or not equal to 0. So what did we wanted, guys? When they are not significantly different from 0, then you can use the model. So when this is the case, AR model, when A1 is equal to 0, guys, what do I conclude? Is there an arc or not arc? Arc or not arc? If the AR is equal to 0, that means no arc. Am I correct? But if the AR is not equal to 0, that means there is an arc. Means if let's say if the AR is equal to 1, so the current variance is related to the previous variance. If the coefficient is significantly different from 0, which means A1 is not equal to 0, then there is an arc present, and correct using the least square means use the arc model. So we use the arc model to predict the future variance. If you have developed two statistically reliable model, that is X and Y, in this case, we want to determine which is the better for forecasting. So guys, if you get the models, AR models from the software developers, you'll have to decide which one is better. You do the out of sample test and you calculate RMSE. The one which has lower RMSE, lower residual mean square error, that is the model that we select. So we calculate the out of sample RMSE, and I will write down, we select the one which has lower RMSE. Clear? Right? Let's see this question. Which of the following is true of modeling a time series that contains two or more distinct period structural change? Okay. They are asking which is true. What is the correct thing? First, the optimal data sample period for estimating the time series can be calculated mathematically. Guys, can we do this mathematically? First of all, we didn't see any formula for structural change. So this is not the answer because there is no formula for as such. Okay, when there is a structural change. To most accurately estimate the time series model, the entire available time series data should be used. Guys, should I take the entire data? Yes or no? If there is a structural change, should I take the entire data? No, we should separate, isn't it? So we have to fit two different models, each for two distinct periods. This is what we do when there is a structural change. They're talking about if there is a structural change. Clear, everyone? Wow, so lengthy lectures, but we were able to summarize and clear everything. This is where we began. This is where I'm going to attach all the formulas. So many formulas we did. Everyone, right? Inculcated the seasonal lag, arc, co-integration. Yes, co-integration was missing in the summary that they said. This is what the outcome is. Now, guys, just a small and very important note for, because we spent so much of time using the regression model and time series. See, if you will see all these videos, what I realized as a student is that first reading, you have to do everything. You have to touch upon everything. Here in quants, the first two topics are almost everything. They are the most important because the other two topics are just theory topics about machine learning and so on. Now, that big data, now many of these things are similar to your level one. They were recently added. Recently means the last couple of years. Recently doesn't mean only in this year, but last couple of years. Majority of your questions are going to be from the first two topics only. So even though they might sound very huge, but these first two topics, suppose if they were split into 5 or 6 topics, you might not feel so much of a pressure. But yes, it's not completely related to your level one. It's related to a topic in level one, which most of us skipped, that is linear regression. So yes, it's a bit complex, but what I've done is that I've covered each and every aspect. So you don't miss out on this. When you are doing first reading, you might have to do along with me, write down the notes, make a chart and everything. It is going to take time. But if you see the overall recording, it's going to be around 7, 8 hours if you watch it at 1.5 speed because I speak so slow. So if you watch it at 1.5 speed, I think you can finish that in 5-6 hours, which is not a bad investment. Okay. Maybe first reading, you might not remember everything. Second reading, third reading, it will be easier, and revision does not take so much of time. So even though it might sound complicated, but the quantum is less. In exam, you might have just two case studies. So 4 plus 4, 8 questions. Out of that eight, this is my view. Okay. 5 to 6 will be from these two topics only. Hardly one, two, or three maximum. I don't think so, three, but if I were an examiner, not more than two, I would put from the other two topics, which is just theory topics. And these topics are crucial. So, yes, first time we are doing everything. Now, many of you all might be like, oh my God, it's so complex. It's so complex. Well, except this is the syllabus. Okay. Those who, those I've seen, those who argue with the syllabus, this is not right. This is not related. They don't become CFA. So we need to respect the syllabus, however it is, however complex it is. So I have to mention all this thing is because I get a lot of text from student, sir, this is so complex. It's not like level one. What should I do? So my answer to them is just do it. Nike, you have to do it. You don't have a choice, right? Because you want to pass. Some things are essential. Not everything might be related to your job, but many of these things will be useful if you're going to be into the profession of CFA. So don't get worried about this. Do along with me. Whatever we have done is more than enough, and the questions that we did are more than enough. Of course, you're going to practice more questions, but this is the bare minimum that you need to do. Okay. Again, I'll repeat, when you probably will revise, it won't take so much of time. Overall, if you see, it doesn't take so much of time. Clear? Got it? Any questions, any queries out here? Let me know. Otherwise, we are done with the major chunk of QM. Now, I'll just put one more input that the rest two topics, guys, if you don't put too much of an attention, if you just summarize it, it's great. Some, risk you have to take in level two. If you have enough time, study everything, no doubt. But if you say that, Kunal, I don't want to push too much of time, I need to do some calculated study because level two is vast, then I would say put 99% of your energy on the first two readings rather than the rest. Got it? Yes. Any questions, anyone? Okay, we'll see in the next topic. I'll see you in the next topic. Thank you.